You can start. You can start, Alwyn.
Good. Good morning, everybody. Welcome to our second session. Well, it's a bit of a marathon session because we chose to try to fit it in before the final round. Well, let's hope for a final round. So let's see. A brief introduction. Just I view the assignment as formative assessment. It gives me feedback, how well did it go last week? And so I must say, I'm a bit, we must recap. So I had lots of assignments handed in where we just had the answers. So it means that my message of it's not about answers, but about structure, didn't really hit the mark. And so we'll just have to try harder. So I wanted to recap without preaching or nagging, but just emphasizing that, but I'm just using that formal quote, but we said there that the important thing is that we reconsider what we teach and how we teach. And so that applies to us. So we have to get out of old habits, just getting answers and being satisfied with answers and saying, this is not our job. Our job is to have a meta perspective on problem solving, different ways of doing it, and looking back and analyzing. And I think I wrote down, so for example, just again emphasizing that it's an absolute must that we do not only work on concepts and procedures, but also on problem solving and logical thinking and habits of mind. And I again use my boxed in and say, if we do not get out of only the black ones and into the red ones, we're boxed in, we cannot improve. And we are here because we want to change things. Well, then we must be open to change and try to change. So let's see how it goes. I emphasize again our attitude of being inquisitive and critical, and that mathematics is beautiful. And therefore, we must develop the know-how and the knowledge and the skills to be inquisitive, to be critical. That means you talk to yourself. You say not just the answer. You must ask, why is it so? Is it really true? And so that must become a habit of mine. And we say we're learning to think like a mathematician. And so my summary, or let me just finish another 2 slides and say, I remind you that we said in the end, it's about mathematical power. And this mathematical power includes the ability to explore, conjecture, make new knowledge, conjecture, reason logically, solve non-routine problems, communicate about mathematics, connect ideas. Now, those are not saying get answers, calculate. We are saying to the contrary. We're saying, and if we think of looking back, and if we think of problem posing, and if we think of the importance of having many different answers, then, I summarize in that and say, we start with our attitude is to be inquisitive and skeptical. That means we want to explain and we want to prove. Well, that means that it can't be answers. It has to be structures, because what we tried to do last week is to show that answers and calculations hide structure and explanation. I tried to show with several examples that when we use numbers and calculations and answers, we just cannot explain and understand why it is so or prove that it is so. So we're doing the wrong mathematics. Just getting the answer cannot explain and cannot prove. But mathematics is all about explaining and proving. And we are insisting on being inquisitive and being skeptical. You know, those two things all the time goes together with me. Our attitude of being inquisitive and skeptical demands that the mathematics that we do must explain and must prove. And that means structure and not answers. It means logical reasoning. Okay, so it boils down to what is mathematics? Calculation, not structure. Explain and prove, inquisitive, skeptical, over and over this. Then I analyzed, not calculation, and we did mainly the first two, that the answers obscure structure and therefore explanation, and secondly, that sometimes it was difficult to find the answers, nearly difficult if not impossible. What I want to do this morning is to look at this third thing that I indicated last week, namely that we have no choice. Induction is a great way to discover new results, but it cannot prove. And mathematics is all about proof. Therefore, induction, which of course works with numbers, which of course will you work with calculations, cannot prove, and we have therefore no choice but to also do deduction. That means logical reasoning. And we must understand the balance between this induction, working with numbers, and deduction, working with logical reasoning. Now, and then I just say with the other thing that we're emphasizing, and we must work hard to develop these new attitudes of what heuristics, problem-solving strategies can we use, but especially this control, looking from the top, thinking about thinking, knowledge about knowledge, self-regulation, to tell yourself, okay, I can do it numerically, can I do it geometrically? I can do it through induction, can I do it through deduction? In other words, talking yourself through these factors of Schoenfeld gives you tools and eyes to look at the mathematics and try new things. I hope that last week we tried to show that we can just decide we're going to try to look at it geometrically, and then it helped us to do things in a certain way that we otherwise would not have done. So it is not just doing the first thing that comes to mind. It's not just about remembering. It's not about drill and practice. It is about being very flexible and on purpose telling yourself that you're going to try different things. You're going to do it. But then you must speak the professional language. You must know what induction and deduction means. Numerical and geometrical, we know that one. And then especially recursion and functional approaches. All those distinctions gives us eyes, new eyes, to look at the mathematics and to do things in different ways. Now, that is what we tried to do with several examples last week. Now, I want to now concentrate on that third problem with mathematics is not number, it's not calculation, and what happens there. Now, I'll start with a quick PowerPoint, and then I'll open an Excel file to talk me through it. So, again, here when I click, of course, you should actually be thinking ahead, and by all means, unmute your microphone and talk and say what you think is going on, what is not going on, what can you do with it, what is not clear, do you have a better idea, do you have just a different idea? That will help us all if we participate. The participation is crucial here. I confess that I find it difficult to handle like that. So I'm going to give you this little example, which if you've attended workshops of mine before, which most of you have, it's old stuff. I believe that The point we're going to make in the next half an hour to an hour is called the pitfalls of induction. And I believe that every teacher should have, I call it little pocket problems. You know, you must be able to just take it out of your pocket at any moment with any class if you want to drive home this point. And this one is one of those, because we have this beautiful, I'm going to make patterns by calculating with only ones. So I'm very quickly running through it. 2 ones is 1, 2, 1, 3 ones. If I square it, you can do it in the calculator. I'm going to use my calculator just now. 1, 2, 3, 2, 1. Beautiful patterns. Of course, there are patterns everywhere. Why do we get this pattern? And is it continued? So if we go for 4 ones times 4 ones, and if we take out our calculator, I'm sure we're going to get that answer, and we can see the structure of that answer. So I am saying what's mathematics all about? Mathematics is when we see a pattern, we think, now how can we use that pattern to solve other problems that we haven't solved yet? So now I'm saying the other interesting thing here is if we now find the digit sum of the answers, then the digit sum of 1, 2, 1 is 1 plus 2 plus 1 is 4. The digit sum there is 9. Check yourself that the digit sum is 16, and check that the digit sum is 25. Okay, now that is called our database. That is very beautiful, but how do we continue? So now I'm asking a question. If we go like 11 ones times 11 ones, can you predict what will the digit sum be for 11 ones times 11 ones? I'm waiting and hoping for somebody to answer. Otherwise, I ask individual people, and then you say I put you on the spot. So if there are any, this is how, if we're more structured, I could now let you complete the questionnaire, then I could see how many people thought this is the answer, how many people thought that is the answer. Anybody wants to put on the mic and say, what do you think?
Alwyn, I see Philip Olifant's got his hand up.
Ah, Philip, so you're here. Good morning. Very nice to have you here. Philip missed last week because of some problems. That means he's here. That means he solved all his problems. That's great, Philip. Okay, Philip, what do you reckon? What do you predict? We call it predict. I can't see or hear you. Did you unmute your microphone? Your hand was up. Do you want to speak, Philip? Hello. Okay, Philip is not responding there. Anybody else?
I know. I figured it out, I think, but I'd rather give someone else a chance, Alwyn.
Alwyn, I think that the middle number, if you look at the answers in the middle column, then
Leon is now describing what patterns he sees. So middle number here is 5.
Yes, and so forth. So the middle number in that next one, the last one, there should be 11. So the digit sum will be 11 times 11.
Okay. Did everybody, now you see that is what we want to speak. Then we said, was the explanation good enough? Did everybody understand, Leon? The 16 one. So you could say 4 ones. So straight from that 4 comes 16. But Leon sees that it is this middle number. See that structure? It goes up 1, 2, 3, 4 to the middle, and then it goes down in the same way. 1, 2, 3, 4, 5 goes up to 5, then goes down again to 1 in the same way. And Leon is taking that 5 squared is 25, 4 squared is 16, 3 squared is 9. I asked for 11 ones, so he's predicting 11 times 11 is 121. Okay, now predicting is one thing. Then we have to learn to check our results and not to wait for somebody else to tell you if you're right or wrong. In my class, I never say you're right or wrong. I say, what do you think? Did you test it? Did you think in a different way? Did you compare it with somebody else's method? Guys, let our microphones just be off unless you want to speak, please. Okay. Any other input here? Then I want to go out. I think I've now learned already that
Hello.
I'm going to stop sharing and then I'm just going to open something else. Who's speaking?
Hello.
Hi.
Hello.
Motimele is
Hello.
speaking.
It's Sekhan. I don't know how to raise it. Mutimele speaking.
Okay.
I'm confused. I don't know why we said the middle number is 11. So what about if we had because there is 11, 10 11s, not 11 11s. So what happened?
Okay, let's look at that. I'm now gonna try to. This damn thing. Just a moment. I'm now struggling a little bit. Yes.
Alwyn, Nico here. I think if you look at the pattern as Leon was talking about, I think it will go up to 9. The induction works up to number 9, but when you get to a double digits, then the pattern ends and something else will emerge from that.
Yeah, okay. Sorry, I now went out. Oh, here it is. Okay. Let me see if I do this one. Okay, I know, but that's very good. I like it, Nico and Sekhana, that we think about reasoning, because this is one of the things, pitfalls. This example is one of those that I think is so often in the media and everywhere, and saying, oh, look at this beautiful patterns, and we must think about this whole concept of continuing the pattern without testing them in between. So I'm just going to first build on Leon's thing on that, and then we take all your inputs is there. So let's understand the structure. So I'm not going to now do that 11 ones times 11 ones. Why is the answer there? Because if we do, this is how we do long multiplication. Some people, I'm assuming that everybody can now see my Excel file, my 111 times 111. Is that all right, Patrick?
Yes, we see.
Yes, Alwyn.
Okay.
Clear.
This is the one
Clear,
thing
Alwyn.
about this damn Zoom. It doesn't tell you that you're really sharing. You're not sure that you're sharing the screen. So sorry for repeating the stupid question. And then if we add that, then that's because we have 1 1 and then 2 1s and then 3 1s and then 2 1s and 1 1. That's why we have this symmetry. Is exactly because of this structure of how we multiply that. So if you now look at a bigger number, I actually have 11 ones times 11 ones there. And if I write it down like that, and then if we add them 1 1, 2 1s, 3 1, 4 1s, then our point is that it looks like it will go like this, up to 11 and then down again, down to 1. And the question is, what is this sum of these digits? We want to see if Leon is right or wrong. And now I'm jumping to a next page and saying, okay, so how do we know? I mean, I'm not very enthusiastic to calculate 1 plus 3 plus, but it's very interesting structure, up to 10 and then 11 and then down again. And So what will the answer be? Well, Leon predicted that the answer is 11 squared. So let's investigate that. And I'm doing that by taking special cases. Of course, because I have this middle number, it goes up and down. So I've had odd numbers, 1, 3, 5, 7, 9, etc. So I'm using Excel to very easily, do the calculations for us. And so I hope you see that, and I'm putting in structure. I am finding there the sum. I'm not calculating it by hand, so we seems to have this pattern. If we go to the middle and then go down, that we're getting a square. And according to this pattern, Leon is totally right, and we will have for 11 ones there, we'll have 121 or 11 squared. And this will be 12 squared. What are you guys saying now? Any comment on this? You know, you see that I love using Excel to do the calculations for me. So we actually have a serious conjecture here, namely that whenever we have this kind of pattern, I could write it down like, if I go 1 plus 2, and I go plus 3 plus 4, to up to anything, and I say n in the middle, and then we go down like 8 and 7, then there's no doubt in my mind that, don't want those two, the sum 1, 2, 3 up to well, let's make that whatever that n, this answer will be n squared. So you see, if that is 10 there, the answer is 10 squared. If that is 8, the answer is 8 squared. And well, I decided I'm a bit worried about this. This is a very beautiful theorem. This is very beautiful mathematics, to think that this kind of structure, when we have this, the answer we're saying will always be a square. Now, is that true or not? It's a conjecture. Now, going back to the very simple start, I was not sure I can manage this. What I want to do is to open my computer calculator. May I now ask Erna, can you guys see my computer calculator that I opened?
Nope.
Or no? That's interesting. How do I tell you what, I can't see the screen. I'll stop share and see if I can share it. All right. Then I will, now I must find it. Screen. How about I share the screen? I'm just trying that. No, I'm not sharing the screen. Okay. You can't see it, but I'm now going to do. If you have a calculator,
We see it now.
Can see it, Alwyn. Yeah, I can see it.
Fantastic. Okay, check me. I'm going to do, and our calculators are not, in the old days, you know, I wrote books about calculators. It could only show 8 digits. You know, the display was very limited. And after that 8 digits, we could do nothing. But now these calculators are so advanced, there's no problem of getting the answer of 11 ones times 11. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm going to take a shortcut. I'm going to use squared, and we'll see the answer. And the answer is 1, 2, 3, 4, 5, 6, 7, 9, 0, 1. I'm gonna copy that and say that is the calculator answer. And I'm afraid that gives us that is a problem, because if we go here, then we'll find, okay, let's discuss this. I'm saying that the answer, I hope I've copied that. The answer is, I can make it a bit bigger. That is the answer of 11 ones times 11 ones. Well, can we do, let's do the sum of the digits. Is the sum of the digits 121? Ideally, you'll be doing it, but okay, I'll be doing it. If you don't mind, I will
No, it's 95.
Excuse me?
I think it's 95.
Yeah, it is something like, you know, I could let Excel calculate it, or I can use my knowledge. How did you do it, Nico?
I just did it. I just added it up mentally.
Yeah, well,
The
we've
old
got
school way. The old
1,
school,
2, 3, 4, 5. I will not do it from left to right, but I'll say it's like 2 times, I think 1, 2 times 1 plus 2 plus 3 plus 4 plus 5 plus 6. Would you agree? I missed it. Is that a 5 plus 5 plus 6? Why don't I make that bigger for us? It's 1 plus 2 plus 3 plus 4 plus 5 on the left hand side, and on the right hand side, and then we've still got other things to do there. Plus another 7 plus 9. Ugh, I didn't want to do it like this, but let me do it. 7
85.
plus 8 plus... I have formulas that I want to do, but I don't want to throw it in. I'm now going to just... I think the answer is 72, but if it's 95, Nico says it's 95, then it's okay.
No, I just did it quickly. I may have been mistaken. I just tried to do it.
Yeah, it's
quickly.
okay. But we know for sure it is miles from 121.
84.
84.
85. 85.
85. Anybody get 121?
85 is correct.
85 is correct. Okay. We've gone. Okay. So we are pushing this idea, guys, that we have this pattern with numbers, and we think that we can make a conjecture and say it's true. But the examples telling us we just cannot do it. Of course, we want to explain that also. The explanation here is that this thing that I wrote down here is absolutely ridiculous. I trust you agree with me. It just doesn't work like that. Do we go count and we say 8, and we count and we say 9, and we count here and we write down 10? That's not our system. Our system is, if we get 10, we write down a 0 and we carry a 1. And we count 11 and we add the 1, gives us 2. And where am I now? I'm about here. We carry 1, it's 10 ones, carried with the 1 I carried is 1. And then I've got the 9 ones plus the 1 I carried is 10. So that explains that 2 and the 0. And it's etc. I hope that is okay. So the correct answer here is exactly as the calculator got. I have now written that down. So this whole this idea that we have 10, 11, 10, 9, 8 there is simply not correct because of the carrying. Sorry, guys, I take it that you have now looked at this thing enough while I was talking to convince yourself. Leon, admit that conjecture is not true. And so it looked very nice when we looked at this pattern, but it doesn't hold. So let me go back. I stop share and now I have to share something else. And I'll go back to this one. And I'm about here. Okay, I think that's about the answer that we had. And so that is an example. Let's make sure what we have here. We had something here that was true and seemed very nice. This middle number 5 gave us the 5 squared. And I trust that everybody now understands that we made a logical error by assuming, because we could see it was true up to 5, that it would also be true later on. But we should all have seen a mile away that this pattern will break down at 10 because of the carrying. Because of the carrying. On the other hand, the other structure that we had there, where we work up to the middle, is completely true. So let's just see if we can prove that before I go to something else. How do we now know? I'm going to again jump around, guys. Yes, it's my calculator. Okay. What do I want to do? I want to go back to Excel. I'll just use Excel to do some calculations for us. I'm just going to, I'll just use this page here. Guys, how are we going to prove something like, I'm not going to write a plus, etc. I'm in a hurry now. Let me make this bigger. I'm just increasing the size of the font to about there. So if we do something like this, 1, 2, 3, y, and I go up to whatever, 20. And I then go down again, all the way to 3 and 2 and 1. Why on earth will the answer be 20 squared? So this is the kind of mathematics we're talking about. Not just calculation, but interesting patterns which we want to explain. Well, sorry, I was hoping to use a superscript. That's better. No. Okay, I use calculator language. $20 squared. Why are we absolutely sure that the answer will be 20 squared? Can you explain why, if we go 1, 2, 3 up to 20 and then down to 1 again, so put your pluses in between, that the answer will be 20 squared? We've seen many examples now, but the calculation cannot explain why it is or prove that it is. Well, let's say for the moment, let's use arithmetic. And what I will do, for example, is to say if we go all the way up to 19 and on this side also go to 19, then if I simply write it down, but I write it down only up to 19. What I'm going to do is to simply repeat this pattern, something like this, but I'm going to write it the other way around, 19 plus 18 all the way up to, let me just now insert some stuff there. Insert, again insert my 19 plus 18 plus 17, and that went all the way up to 19. Damn it. Let me try again. I'm going to write all the way up to 18 and 19 and leave the 20 there, and then on this side go all the way 1 and 2 and 3 and 17. I trust that you understand what I'm doing now. I'm just rearranging it. So I am writing this, I'm taking the same sequence up to 19 and writing it below it, but this time the other way around, and then I'm going to add them, and then I'm going to get 20 and 20 and 20 and 20 and 20 if I add them. So the total surely is 20 plus 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 20, 19 times plus the middle 20. This is the middle 20. I had 1 to 19 in front and 19 to 1 at the back of the 20. I hope this explanation helps. Now I'm writing it below each other and I'm adding them. And I'm getting and I'm getting 20 plus 20 plus 20 plus 20, 19 times plus that 20. That will give me 20 20s, and 20 20s will be 20 20s will be 20 times 20. I shut up for a moment and ask if anybody wants to make an input here. Let us get the difference. Previously, I tried to make new mathematics by looking at the patterns in the numbers I got as answers of calculation. Now I'm concentrating on the structure, because although I'm going from 1 to 19 and to 20, this really doesn't matter. I can go to any number that I like. If I go to 78 and I say that that is 77, and that is 76, and that is 75, and I say that is 77, and that is 76, and that is 75, and I add it up, then I'll get 78.
Alwyn?
Yep.
I just want to come in over here.
Go.
I think this is a lovely example to do with our primary school teachers. And even the learners, when they look at this technique, it's such a wonderful technique for them to learn at primary school level, because they will come across it in grade 11 and 12 when they do some of an arithmetic sequence.
This is exactly the proof of the formula for the nth term of an arithmetic progression. You write it down, sum to n terms, and then you write it down again the other way around, and then you add them. It's exactly that. So it's really Gauss, the first and the last.
Absolutely.
We could really work with the first and the last, no problem, but I don't want to work because of the odd number and all that. So 1 plus 77 will give me that 78. And the 76 and 2 is 78. We could really use Gauss here. Agreed, Nico?
Yes,
Um,
yes, yes.
But it's just more convenient. Thank you. Continue if you want, Nico.
No, what I'm saying is that this kind of technique is exposed to, I'm not even looking at teachers. I'm looking at the learners, the children.
Yes.
Because I work with the children, and I'm telling you that they get this kind of training and background at grade 5, 6, 7 level. It'll be so wonderful when they get to high school. In fact, they have told me, many of them that I worked with have said that, quite a bit of what they've done in primary school has helped them in high school. So we mustn't look at it upon, like it's two different kind of mathematics. The mathematics that they do in the primary school is so fundamental to what they're going to do later on. And these kinds of techniques will only enhance the learning of the children and even our teachers.
Yeah, I'm not mad about technique. Remember, everything boils down to the structure of mathematics, and the structure has all to do with the properties of the operations, namely commutativity, associativity, distributive property. So if I want to add from 1 to 77, why will I start the first and the second, etc.? So the order doesn't matter. So I can add that's Gauss, the first and the last, the order, and I group them differently. So the commutative property is immediately on the table. The associative property is immediately on the table. If I say in the case in front of us that I have 78 78s, it's repeated addition, so the definition of multiplication is on the table. Guys, we're doing fundamental mathematics by using all the structure and not doing simple calculations, step 1, step 2, step 3, that we do not understand. So this whole discussion here, I could have done it better, you could have done it better, is to emphasize that careful, when we work inductively, that's what we did with the 1, 1, 1, 1, 1, 1 squares. We worked inductively by working systematically with special cases from 1 to 5. And then we thought we saw a pattern, but our pattern was false. So I'm now again going to go out here. Any other input? Okay. So this is a little problem that we can all use when we want to convince learners that I want to emphasize that this induction, we've done this before, but I want to emphasize it again, is I just need to move stuff out of the way here. I'm just going to use a pen. I want to emphasize that induction consists of 2 steps. First, this is our database. We had this 1, 4, 9, 16, 25. Only this 5 numbers. And so the first thing, let me see if my pen can write. The first thing that we do is we find a pattern. We call it abstraction. We're very good to be able to see the pattern here, 1, 4, 9, 16, 25. So we identify them as squares. So we see the pattern. That's step 1. That usually is correct. No problem. It's absolutely correct that all of them are squares. In all cases, the whole thinking behind induction is that you have such a database. You find a pattern which is true for the database, and then in step 2, you extend it, you generalize it. The problem is, do you have the right to think that this pattern is continued? We didn't do all the calculations all the way up to 11 ones. No, we say on the basis of what we see, we think that this pattern is going to continue. That's very important for us when we do mathematics, that we do it. but we must understand its shortcoming. Its shortcoming is that it's not always true that that pattern is continued. So here exactly you find that it's not true that the pattern is continued. But in my other example of 1 plus 2 plus 3 plus 4 plus 5 plus 4 plus 3 plus 2 plus 1, of course it is 5 squared. And we've now shown with a general reasoning that it will hold. So the reasoning with deduction is different from this induction. So we're always going in induction not sure if we made a mistake. Either our recognition of the pattern may be wrong, usually that's not a problem, or secondly, our extension may be false. We may not have, so if we do not have structure, guys, this is the next part that we're going to work. If we do not have a structure that proves that we may continue the pattern, we're going to make mistakes. And we make mistakes all the time. So let me continue and say also, if you at workshops, there's another little pocket problem. I think I can do it better than that. Okay, have you got that? I start with a polynomial n squared minus n plus 11, and we are simply going to calculate the value as n goes 1, 2, 3, 4, 11, 13, 17, 23. Of course, we're making mathematics all the time, so can you conjecture what kind of numbers are these? I'll take an input.
Prime numbers.
I didn't hear.
Odd numbers.
That's one. Anybody else?
The first few are prime numbers.
Prime numbers.
Prime number.
Prime numbers. Okay, well, so here we have step one. I'm not going to scratch on it, but it's clear for you. Step one, we've got 10 numbers in our database from 11 to 101. And we're looking for a pattern in this. We're looking for a pattern in these numbers. And there are different patterns. Our first one says it is a square. That means you're going to say in this 10 numbers, no doubt these are all squares. Now we say, therefore the answer is always a square, no matter what n is. If n is 20, 30, 100, it will be a prime number. Maybe I said something wrong just now. Always prime. Always prime. You can see in front of your eyes, it's always prime. 17 is prime. 23 is prime. 53 is prime. 83 is prime. 101 is prime. Everybody happy with the great mathematics that we're creating?
Yes.
Happy?
Yes, sir.
No, good.
Happy.
Happy, everybody happy. Remember, what did we say? We said,
Happy.
look here, in front of your eyes, if we calculate n,
Everything is prime.
of course, there's another pattern which we can, I long ago didn't really calculate. I saw that there's always plus 2, plus 4, plus 6, plus 8, plus 10, plus 12, plus 14, plus 16, plus 18, and the next one plus 20. So actually, I was using that pattern when I calculated it. Is that pattern true? So our reasoning was to say, here I've got 10 examples. We see, we can apply our knowledge and see that in all cases the answer is a prime number, and therefore we've got this new theorem. The answer is always a prime number.
Prime number.
But what you must do, remember, a mathematician, the characteristic, the attitude, the habit of a mathematician is that we're skeptical. We do not believe anything until we can prove it. So I think we must learn to be a bit skeptical and say, oh, that's so nice. N squared minus n plus 11 is a prime number no matter what the value of n. Is it really true?
No.
How do you test it? Well, one of the most basic ideas of testing is simply to use a special case and find the so-called counterexample. So I'm just going to go on. The database is up to 10, so let's go for 11. Well, if I do it for 11, we don't really have to calculate because minus 11 plus 11 is 0. Answer is 121. 121 was never prime, ever. It's 11 times 11. So, sorry guys, the reasoning was false. The reasoning broke down. And I trust you understand why. You can't have even 10 cases. It's not good enough. So even if we, no matter how many cases we have, we cannot be sure that this pattern is continued without having a structure to tell us how it is continued. Any comments on this? Another one that you can remember quite easily.
Alwyn,
Yes.
Alwyn, I just want to add here that obviously if we have come up with a formula that would depict or come up with prime numbers, we can probably win, the Nobel Prize for mathematics.
Yes. Every math teacher should know it. There is no, let's be sure there is a pattern, but there is a formula, but no, not a polynomial, nothing like n squared or 5n times 1 or 5n plus 1 or something like that. There is no such a pattern. No. Okay. I could. So this whole structure, if I again just try and open an Excel file, if I can see it. I have so many stuff in front of me. Not there yet. Excel. Looking for my Excel file, not roots yet. I don't want calculator. I don't want those squares. I don't find it, so it's okay. I'll just go back to the PowerPoint and continue. Okay, so now let's not rush. Let's stay here and say, but there was another conjecture as well. There was a conjecture that the answer is always odd. Now you see, this is what I want you to understand, and what we simply have to manage. I'm a bit fast. We saw that with 10 examples, we couldn't be sure that the answer will always be prime. Well, surely you understand that with the same 10 examples, we cannot be sure that the answer is always odd. But we don't want to throw away all the answers just and say, we can't be sure. We want to make sure. So again, can we be sure? How will we be sure? How about I let it hang for a moment and say, can you convince somebody that n squared minus n plus 11 must always be odd, no matter what n? How can we do that?
You can do that, Alwyn. You can.
Okay, I'm just, everybody think on that for a moment. I'm just going to try to see, I can't remember where is that calculator I want to use.
Oh,
Okay, I'll use this. Maybe this will not be so clear to you. I'll just want to illustrate that you'll remember that we started with this 1 plus 3 plus 5. Let me sure you're seeing my Excel file now. Yes. So 1 plus 3 plus 5. The answer is there. Always a square. Always, I wrote it as squares. And you know, we can go on here in Excel. I can go down like this. And remember, Excel has calculated it for us. All the way, I could go much further, but here in Excel, I went all the way up to 10,000. So I've got 10,000 cases that if I add 1 plus 3 plus 4, sorry, let me try again. 1 plus 3 plus 5 plus 7, all the way for 1,000 numbers, the answer will be 1,000 squared. Still, I'm saying that we cannot be sure that that is correct, not for 1,000 cases. Similarly, if I look at a new problem, the new problem, if we find the sum of 3, I'll just go back to the top. If we find the sum of 3 consecutive numbers, 1 plus 2 plus 3 is 6, and 2 plus 3 plus 4 is 9, the answer is always a multiple of 3, and I can go way back all the way to 1,000, and the answer will always be a multiple of 3. But in mathematics, we cannot be sure that the next one will not be a multiple of 3. So this is what it is all about. I go back to the top and say I can't remember what I have here, but the third one was exactly this minus n plus 11, which is true for 101 up to 10, and then the next one and the next one are not prime. But I'm saying that if we make a new problem and if I ask, is it always odd? And I would write here, I think I made it all white, yes. Then this answer is always odd. There, all of them, all the way down to 1,000. I have them, and you can check. This is an odd number. All of them. All of them. I'm substituting that value into n squared minus n plus 11. And the answer is always odd. The answer always goes like 1, 3, 7, 3, 1. And then it repeats. That's another pattern. So my point is that just because it's true for 10,000 cases, that the answer is odd, we cannot be sure that it is odd. So my question, and now I answered it, and then we continue, please. Well, I couldn't show that if something is true for 10 values, it's always true. I couldn't show that if it's true for 10,000, it is always true. For how many must I prove something to know that it's always true? For how many cases must I prove that it's true to know that it's always true?
All cases.
Exactly, all cases. Well, that's why we do algebra, because if we say n, it becomes any and all. But we have very powerful ways of working with this. So I'm going to try now to, it worked last time. I'm going to try to open my writing pad. Can you see my, can you see my writing pad?
Not yet.
Not yet.
Okay, probably I have to stop sharing and find it and open it. Okay, now you can see it.
Not yet.
That is the old one.
Let's minimize this one.
Not yet. We're seeing your Excel.
Okay, sorry, it's a question of looking. I stop sharing. It is open, so I go to share screen, but now I must find it. It's not that. It must be this. I ask again.
Yes.
You see my drawing?
Yes.
Okay.
Yes, Alwyn.
Thank you. So let's just do it very roughly. Okay, I have got this low battery thing, which is, I'll see how long my battery lasts. We've got n squared minus n plus 11. How do we use the structure to show that it is always odd? Well, I'm going to suggest we don't. I could manipulate. I love, but I don't want to assume any high school mathematics. But if I factorize it like that, we've got two consecutive numbers. Well, if we have two consecutive numbers, then the one is even and the other one is odd. Would you agree? Come on, 2, 3.
Yes.
3, 4. So it doesn't matter if n is even or odd. If n is even, then n minus 1 is odd. If n is odd, then n minus 1 is even. So that first number is either an even number times an odd number, or it is an odd number times an even number. And then we're adding 11 to it. But what can you say? Are you sure about an even number times an odd number? Any even number times an odd number. Well, if you haven't thought about it yet, then you try it now. What can you say about an even number times an odd number? So if you had 2 times 7, the answer is 14. If you have 4 times 11, the answer is 44. Which ends always in 4. That's not the concept. If you have 10 times 13, you have 130. I would say that it's very obvious very quickly that if you multiply even times odd, the answer is always even. Would you be happy with that? So that I can say that is always an even number. I only looked at the first. The answer is always even plus 11. But of course, 11 is an odd number and you don't even have to work with 11. So what can you say about an even number plus an odd number? Are you sure you can generalize and be sure that if you add any even number plus any odd number, the answer will always be... And how do you find out?
Alvin, let's take 2 times 3.
Yeah. No, I'm already past that. I now want to know what's an even number plus an odd number. I say this even number times an odd number or an odd number times an even number is an even number. Now I'm going to add 11 and 11 is an odd number. So what's an even number plus an odd number?
I see a picture.
Odd number.
Dots in my head. There's sort of dots where there's an odd one out with the odd numbers.
Yeah.
So you. I take
it's something. Yeah, it's something like this. Thank you, Erna. This is what I feel. If we can just get comfortable with this, you don't just know. You say, "Damn it, can I make a sketch? Can I make a representation? Can I think geometrically? What eyes can I put on?" Then you're thinking structurally. You're not thinking what's the answer. And so I want to say I can go on with twos like this, and I'm going to say this is any, I'm not saying how many I repeat. I'm just saying they are all pairs, then surely it's even. And if I now make sure that I do the same, and I make pairs, and then let's lots of stuff in my way, so let me choose a different color, and I'd say, and there's an odd one out. Do we agree? Then this would be an odd number, because that's what an odd number is. It has pairs, and then there's an odd one out. But this even number have only pairs. It's 2 times something. It's an even number. And then if I add them, I just push all of them together. And you're saying that if I push them all together, I'm going to have pairs, red pairs, red pairs, red pairs. But there will be this extra one blue counter or marker or dot or chip or whatever. And that's clear that that must be odd, not so. This will be odd, because that's what an odd number is. It is a lot of pairs plus an odd number out. Now, I'm claiming that this reasoning proves that the answer will always be odd. That is always an odd number for any value of n. So when we said prime after 10 cases, we showed that it was false in the 11th one. So even if we have 10,000 that is true, we can't be sure the next one is true. But if we reason abstractly like this, then we can be sure. I just want to make sure that you don't think that that was now high school stuff, because we could simply, I'm just trying to move stuff away here. Okay, for example, there was no need to really factorize that. We could simply say n is either even or odd. So if n is odd, then we would have an odd number times an odd number minus an odd number plus an odd number. Now, I'm challenging you to say, and of course, n doesn't have to be odd, so that means I'm saying n is 1 or 3 or 5 or 7. But why not 2 or 4 or 6 or 8 or 100? So it could also be even times even minus even plus odd, of course. And so you just have, how convinced are you that an odd number times an odd number, like 3 times 3 is 9, 5 times 5 is 25, 11 times 11 is 121. I have no doubt that we can easily show that that is odd. And we can easily show that this is even. Okay, then an even minus an even number will of course be even. And if you add an odd number to that, then that will be odd. And you must just reason the same here. An odd number minus an odd number, well, maybe you should just check. 7 minus 3 is 4. And 13 minus 9 is also. Why do I love 4 so much? And 25 minus 16. What am I doing? Stupid. Sorry. 25, say, minus 11 is... I really love 4s. Is 14. So an odd number minus an odd number will always give us an even number. So this part is also even number. So we can very easily reason why it will always be an odd number. So we have a very interesting case to my mind, where the same thing, where we show that we can't say it is prime through induction, And we can't say it's odd through induction, but when we use deduction, that means logical reasoning, we can prove that it is always odd. Always odd. Okay, any inputs on that? Okay, I'm going to go out.
Sorry, Alvin, just one thing. Just as a class discussion, you can change the last number, make the last number even, and then ask the children to discuss that. What will happen? What changes? And you know, they will obviously come up with different conclusions.
Yes, yes. There's lots, as I say, really, guys, teachers should know all these questions. So I'm just going to, again, I'm just removing stuff here. I'm just going to emphasize that, for example, if instead of 11, we use 41 there, it is, as a matter of fact, prime. That is prime, 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 prime. And they are all prime all the way up to 40. So here's a case where if you use that, then it's true for 40 cases that the answer is prime, but for the 41st, it is not prime. Okay. And then, as Nico says, using other kinds of numbers. But you see, really, we should do much more than in the primary school, working with numbers. So such things like an odd number times an odd number is always an odd number should really become obvious in the primary school, and not only know their tables and could do long multiplication. We should be thinking at a different level, especially odds and evens, because that empowers us to do a lot of different things. Okay, and I trust you understand now what was the point of me writing these examples, which breaks down after 10 or 40 or 10,000 or 10 million cases. Guys, even if something is true for 10 million cases, we cannot say it is always true. Okay, so let me just now go back to my PowerPoint, which I must now find. Okay, it's this one. Okay, I'm finished here. I'm sure that you've seen this one many times before, so if we can rush through it, then I call this points and regions. I'll share the PowerPoint and the video afterwards again, but it'll be great if you work ahead. So we've got this question here of certain number of points. If I have 1 point, how many regions do we? If we understand the regions, there are 2 regions. There's only 1 region. Here are 4 regions. That's a region. That, etc. So I completed the first 3 for you, and I'm asking for 6 and for 20. And so if you don't mind, I very quickly, for 4 points, I'm calculating there. And there we go, 6 and 8. And of course, we're very happy because we see this pattern. And even if you do it for 5, I'll very quickly do it for 5, blah, 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 blah. You check if I'm right, that the answer is 16. And now, you know, this is the mathematics we do every day. And now if I ask for 6, we probably will do something like this and say, this is our database. I hope you understand that word now. That means our experimental values, we know it's true. If the P is 2, R is 2. If P is 4, R is 8. P and R is the number of points, the number of regions. This, all these ones in the database, this is true. The question is it true? If we continue recursion, we would predict that, and if we use the function, in both cases, we would predict that this is 32. And even later on, if I use that formula, we would predict 2 to the power 19. Then again, the question is that true? Well, we would be very sure. We can see pattern, damn it. Everybody can see the pattern of times 2, times 2, times 2, times 2. My point again is, of course, it is true in the database. But assuming that it extends beyond the database without really testing it is an assumption which we cannot know for sure is true. So if you don't know the example, I'm suggesting that it's one of those pocket problems that you simply have to know and be able to take out when you need it. You know what I'm talking about? I mean, when you're going to, in grade 11, prove sine squared plus cosine squared of theta is 1, and the child said, well, the sine of 30 plus the cosine squared of 30, then you have to give them 0. You can't say it's nearly right.
It is 1,000.
It is 0, 0, 0, 0. You cannot, because it's true for 30 degrees and 60 degrees and 45 degrees and 90 degrees, say that it is always true for any value of theta. And we have to convince our children. But we must do it in grade 5 and 6. We cannot wait until grade 11 for children to understand this very basic underlying structure. So let me put my money where my mouth is. Obviously, if you saw me, you would have said my body language is quite clear that I'm saying we all would think that the answer is 32 for 6, but it's not 32. It's not 32. So here I have in front of us, I drew 1, 2, 3, 4, 5, 6 points, like we have here, 6 points. And these patterns predicted that there are 32 regions. And so let's check if there are 32 regions. How many regions? I'll be slow for you to make sure that I'm not cheating. There it is, counting all the regions. Counting, one by one. I try to be systematic. 26, 27, 28, 29, 30, 31. Sorry guys, did I cheat somewhere? The idea of maximum number of points, the maximum number of points is here in the 21. The only thing about the maximum is we must make sure that 3 chords don't pass through 1 point, so I could easily have drawn this chord through this point, and then I would have missed this extra region here where we have this small little triangle, and that after 6 happens more often. But I'm just going to make sure that you are with me. Our number pattern extension predicted that 1, 2, 4, 8, 16 surely now will be 32. But it is not in this case. In this case, 31. Well, if you're going to prove for 7 points, again for 7 points, just going back again, just to remind you what we're doing, would you say for 7.64? No, there's a different formula. It will be in our notes. There's another formula here. I don't want to take it out now. So just to click through, I am finished there, and now I'm asking for 7 points, and I'm going to count very quick. We have definitely not 64, there's 57, so there's some other formula here. The mathematics is quite different here. So this was not 31, but 32. Induction breaks down again. So just after 2, 4, 6, 8, really, 2, 4, 6, 8, 16 didn't continue to 32. So this is the part of mathematics that I'm putting in front of us to emphasize again that calculation and answers and numbers are problematic in mathematics. Without structure, we can do absolutely nothing. Now, bearing in mind that we want to take a break, I'm going to quickly show you some more examples. You will have the PowerPoint and the video, but I mean, write down and participate yourself as much as you can. I remember that I called this an IQ question, and then I think Erna and other people said, no, I'm playing with fire, But, where this kind of question where we say, what's the next number? Complete. And even in grade 11 and 12 sequences and series, we think, I always classify them as IQ questions. But forget the IQ. It's not that your IQ is high or low. The question is, what is the next number? And, I must say, probably you guys are saying, what does this guy think? We're stupid or what? Because we'll all think that we can give the right answer here. Well, let me make sure. Can anybody tell us what's the next answer, please? The next number? If you go 2, 4, 6, 8, and then continue. Anybody wants to stick out your neck?
Who do we appreciate?
Come on, just be active. Okay, thanks, Mark.
It's 10, Alvin.
Yeah,
10.
10. Okay, 10. I failed this one. 10. Where do we get 10? Well, 10 we can get in two ways. If we make a table, then I'm going to say, if you work, we must understand. This is our database. This is true. It's true. 1, 2, 2, 4, 3, 6, 4, 8. It's true. We gave it. It didn't say first, second, third, fourth. We are imposing structure.
Someone's mic is on and making a bit of noise.
I can double the point.
Well, yeah, okay, but guys, don't. I appreciate it, but you must build on the ideas. Don't say something new. As long as you build on the idea, you're welcome. But now come, you're not thinking about what I am saying, then I'll think what you are saying. First this one, then we'll take yours. Of course, I anticipated that. The point is, I'm saying that one way of doing this is to say plus 2, plus 2, plus 2. If we say plus 2, it will be, or we can say times 2, times 2, times 2, times 2. That means basically that we say we have a formula 2n, because 2n means 2 times n. And then n is 1, 2, 3, 4, and then the answer will be 2 times 1, 2 times 2, 2 times 3, 2 times 4. So there are two ways, but both ways says that the answer is that this continues to 10 and then to 12. I trust that we agree with this distinction between recursion, call it horizontal, and function, call it vertical if you like. It's very important. So the question, you see, this is the problem with induction. In our database, both patterns are true. Plus 2, plus 2, plus 2. If you work with a sequence, or times 2, times 2, times 2, times 2 if you work with a function. But the question is it true outside this red ellipse, this database? And I say most of the time we assume that it is. But it's a false assumption, and we must get rid of it, because that's arithmetic, and we are doing mathematics where we want to reason. Okay, I'll show you that it's no way obvious that the next number is 10. For example, I know this is very cosmetic, but I made this complicated formula, 2n, gives me 2, 4, 6, 8, and the 10, and the 12, of course, wonderful. But I make another formula, I just make it. 2n plus n minus 1 times n minus 2 times n minus 3 times n minus 4. I'm going to say, also gives me 2, 4, 6, 8, but then not 10 and 12, but 34 and 132. So which formula is right, that one or that one? Well, you see, if we don't have a context, we do not know. So I'll just make sure that you understand why we're getting these answers here. So if we, in this formula here, in the second formula, substitute n is 1, then we get 2 times 1 plus naught. If n is 1, that's naught. Naught, well, naught times anything is naught. I trust you're following the arithmetic there. And so we have just simply constructed a formula where this second term, n minus 1, n minus 2, n minus 3, n minus 4, one of them is 0, and therefore it gives the same answer just as 2n because the second part is 0. So that's why I get my 2, 4, 6, 8. But the moment I say 5, it is not 0 anymore. And now we've got a problem. So that's the 2, that's the 4, that's the 6, that's the 8, that's the 34. So this formula, bottom one, says the next number is not 10 but 34. The point is that we just cannot know which one of these two is right unless we have some structure. Okay. And that means that mathematics must be about structure. If we do not have structure but answers and numbers, we cannot be sure. But mathematics is about being sure. Mathematics is about proof. So I said we change what is mathematics. Mathematics is about proof. So sorry, it was not that obvious that the answer is 10 and 12. It may as well have been 34 and 132. Next one, 1, 2, 4. Next number. You are thinking something.
It's 8. 8, Alwyn.
I've got 8.
No,
I've got
not
8.
8,
I've got
Papa.
8.
Wow.
Okay. Is that all? Nobody with a different answer?
That's 18. 12.
12. It can be anything. Anything.
0.
Okay, let's take this function idea 1, 2, 4 again. This is the database. It's true. The first number is 1, the second number is 2, the third number is 4. Where does it come from? So what's the fourth one? That for the database we have that. So recursion will be times 2 times 2 times 2 will give us 8. But that's not the only way. If we work with a function, then that would be 2 to the power 1, 2 squared. What am I saying? Yes, it's correct. 2 squared is 4. 2 to the power 1 is 2. This one you may not know if you're only in the primary school, not to worry. But you see the pattern, we impose structure. Both of them says the answer is 8. But why? In both cases, we are extending the database without having the right to do so. And so we do not know which one it is. So I'm going to say, but it may as well have been plus 1 plus 2 in the recursion. That's right. Plus 1 is 2, plus 2 is 4, and then plus 3 is 7. Why not 7? Which one is right? Can we know? I just wait for a while and ask if somebody wants to comment on in front of us which one of these two will be right, and when do we know which one is right?
They're both right.
They're both right. In this case, when we have abstract number without a context, we cannot be sure what is the structure. We do not know. In both cases, it's true for the database, but we do not know how it is extended beyond the database. We do not know on what assumption we have the right to say that it continues to say times 2 or continues to say plus 2, plus 3, plus 4. We just don't know. But I'll show you 2 examples. I'll show you, here is the formula. I don't think I need it. But without context, we don't know which one. But in a context, for example, very quickly, what is the maximum number of regions in which if we have 6 chords, so we have 1, 2, 3, 4 there, and 2 there, and 1 there. So in that case, we've got 3 chords. Again, we must make sure that we don't draw them going through one line. So I said, it may not be like that. And I said maximum number. It may not be like that. And it may not pass through the same point, but it must be like this. So there would be only 3 regions, but here is 4 regions. So if we say 4 regions and we count it, then if we have 4 chords, we know it is 7, not because of the number pattern, but because the structure of the situation. In this case, it is quite clear that for 3 chords there, the answer is 7. You can see it is 7. So it must be 7 in this case. That's the correct answer. Not so. The correct answer here in this table is 7, because the structure of the situation says it's 7. But here's a new problem. What's the answer? Well, if I say the substance doubles every hour, and if it starts at 1 cubic centimeter, what's its volume after 2 hours, 3 hours, 4 hours? It doubles, doubles, doubles. Then surely doubles, doubles, doubles. No doubt about it. The answer would be 8. In this case, 8 is correct. In the previous case, 7 is correct. You just cannot say which one is correct. I'm saying all this to motivate that mathematics is about structure and that we should stop doing calculations. We know it's 8 not because of the number pattern, but because of the structure in the situation. We've already had that. I say the problem is with induction is if one sheep is black, if I see 1 black sheep, if I see 2 black sheep, if I see 3 black sheep, and then I say all sheep are black, just because I didn't see a white one. But that's not logically true. I just have to see what I have now. Okay. It's 9:40. Right. Erna, you want a break now or after the next example?
No, I'm still fine.
Okay. We had this idea of the flipped classroom, where we give homework not as practice examples, but as developmental examples. I'm now into roots, which was our flipped classroom activity, which means you have now thought about it beforehand, instead of me dumping this example on you suddenly. You have now had time to look at it, and I wonder if somebody wants to make inputs in this regard. I think that I decided this morning that I will put it in an Excel file, so I just have to now find it. Just want to check if it's open. What am I looking for? I'll just make sure that I open it. I must open the roots. Excel file. And now I should be able to see it in Zoom, if I can find it. I find it. I remind you of the problem. The problem was to puzzle out the number of roots between A and B, and the number of roots between B and C, and the number of roots between A and C, And the question is, how do we approach it and how do we solve it? This is a question of, it's all about our heuristics and our control and implementing those, and not about remembering some kind of formula that if you may be teaching at a higher level that you can impose on the structure here. I'm going to suggest, so I did say, and I'm serious, it will help a lot, that instead of me, when I start off with this, I'm gonna start off this problem by looking at special cases and studying how many paths are there in the first block and then 2 blocks, etc. But I'm saying in the flipped classroom, you had time to work on this. Is there anybody who wants to explain something about how to attack this problem? How did you attack it, as a matter of fact? What knowledge could you bring knowledge to the situation? Could you implement some heuristics, like try special cases, be systematic, make a table? What control could you exert? Could you say that it's going to take too long, it's going to be too difficult, you're rather going to try something else? Did you change strategies? We'll want to think like a mathematician. Anybody wants to make an input of how they solve it? I have a few very interesting submissions. Okay, then I'm going to basically show 2 things and you can build on that. I'm going to say I actually don't know how to do it, and therefore I fall back on induction, and that would mean trying special cases. So I'm actually going to count and see if there's a pattern in the number of paths in this sketch that I made. So I've got the sketch here, and what I'm going to do is to make a table and try to be systematic. And to do that, I need to introduce some notation. And so I'm going to introduce notation like that, not to worry. I'm just marking all those corners because I need to record it, to know and to check that I'm right. And actually, this thing I've made up to 12, so I had a problem in the beginning, so I didn't mean to start off with this, but I now must because of my programming, and that is that I'm going to describe the size in terms of blocks. I must say that many people have a certain interpretation, the everyday interpretation, and counting this square as a block and this is a block, and saying that this is 4 blocks. I actually defined the length of from A to D, that unit, as a block. So actually the length of AD is my block, but it doesn't really matter. So what I'm showing is that from A to D, there is only one route. If you travel from A to D, remember we're on our way to travel from A to B along the shortest possible route, and that means I travel from A to D, and there's only one such route, straight from A to D. If I travel to E, that would be, I called it 2 by 0, so going right and down. So my size description is going right and down. How many right, how many down? So I go 2 right and 1 and 0 down. To go to AH, from A to H, I go 0 right and 1 down. So right at the 0, 1, get the difference between 0, 1 and 1, 0. That's the start. 0, 2 would be 0 to the right, and 2 down would be from A to I. So you go straight from I to I. You get one route in each one of those cases. So on top there or on the side here, we'll have only one root in each case. So let's start something more complicated. See, if I take a 1 by 1, if you want that block, in other words, going from A to L, I'm not going to, if you like, I'm listing the roots. I'm going to go very quickly because you've worked on this yourself. I'm hoping to find some pattern, and you can tell me what patterns you found. If I go in this one block, this left one, ADL, if I travel from A to L, this notation A to L means I begin at A and I end at L. There are two ways I describe it as ADL, that's one to the right and one down. That's a root. I did write already to some people that they had problems here because they didn't understand the concept of root. We didn't say just on the sides, in all the different possibilities. But you could also go AHL, so it's obvious that those two roots, ADL or AHL, I could use some color here to show that, and many of you did. B used some color to show her paths. That would be for a 1 by 1. And then I'm going to try to be systematic. My next, I'm going to do a 2 by 1 going from A to M. That means I'm looking at that 2 by 1 blocks. I've got a 2 by 1, and now I must carry the different people have different ways of counting them. I named them AEM. I went from A to E to the right, then down to M1. ADLM, sorry for that long one. I went to D, then down to L, then to M. So I went that zigzag. ADLM. I had to use them all. I could go down to H, and then I'm not going to say L now. I go straight to M. So I had those three roots when I had the 2 by 1 block. I make more 3 by 1 block. I'm going from A to N like that. And then you can see the path. I hope you see that you can now check me that for those, that 3 by 1 block from A to N is the opposite corner. We'll have 4 different paths. And in a 4 by 1 block, which I trust you understand is that block. No, 4 by 1. Yes, it is AO, from A to O. You will see that it is actually on top it's 4 by 1. It looks like 4 plus 1 is 5. And in the previous case, 3 plus 1 is 4. And the previous one, I see this pattern between actually all of them. But of course, it's wrong before we start. In both cases, it's the sum. 1 and 1 is 2, 2 and 1 is 3, 3 and 1 is 4, 4 and 1 is 5. So several people thought they could find a pattern between the length and the breadth of such a block. But of course, it's already dead because that is not true for my 0 cases up there. Or is it? No, it's not. One more. It's not the sum. 0 plus 2 would be 2. That should have been 2. It's 1. So that pattern will not hold. So you don't be surprised when we get to, I'm just working in the opposite direction. And now I have a 1 by 4 is from there to there. 1 right and 4 down, which can be easily counted. You simply, if you go right, you go from A to D and then all the way down to X. If you come left, you can stop at H, go right and then down. from A to I and right and then down to J and then right and then down from A to K, then down to X. I said I'm not even listing them because this 4 by 1 is the same. This 1 by 4 is the same as a 4 by 1. So I already made this assumption that the 4 by 1 is the same as a 1 by 4. I didn't list them. I know that the answers are the same. Do you think I'm justified? So there's no surprise that if I do a 2 by 2, the answer is not 2 plus 2 is 4. Guys, many people got 4 for an answer. It's not. I assume that if you look at that 2 by 2, if you look at my list of paths, that you understand my notation and can count it to 6. And I think I do one more. A 2 by 3 was quite laborious. A 2 by 3 would be 2 right and 3 down, would be from A to T. I could go 2 right all the way down, or go to D, then to L, then to M, then down. And there would be 10 such different ones. You could compare the 2 by 3 block with the listed routes and count them, and there are 10. And I must tell you that's why I gave, because I did not see an arithmetic pattern between the size of the blocks and the number of routes. I gave up and decided I cannot work like this, and I decided I better now start using the numbers that I used. So I'm very explicitly using the numbers. We don't have a straightforward a table in this case. So I just need to, am I in Excel? Okay. Just trying to get something to write with. Damn it. This damn thing is not going to let me write. Okay, unfortunately, I'm not sure why. Okay. Nope. I'm not managing to write. Okay. Right. I'm now going to say that it would be, I'm trying once more. Nope. It's okay. We'll come back to it. I am now going to do two things. Before I write down those values there and work with it, let me just make sure. If you want, what I'm going to do is to actually simply, I'm trying to take a shortcut here and say here.
That was the hardest thing to do, to turn that.
Say again, Erna. Say, I'm listening.
I say that was the hardest thing to do. It took me a full day to manage to turn that square.
Yeah. Sorry, it's certainly my damn. I don't know where is my Excel file now.
Why do you make it? Why don't you snip it and then draw on the snip?
Yeah, never mind. I'll just stay here.
We are seeing your Excel.
Yeah. Okay, no, it's not right. I'm not seeing my Excel. I'm going to say stop share, then I'm going to say share, then I'm going to find it. I'm going to open it. And then I'm going to go here. Okay, I'm going to cheat and say I'm not going to work like that. I'm going to work like this. And you will be surprised that what we have there, the numbers that I calculated, as a matter of fact, there was one root there, one root there, one root there, one there, one there, one there, one there. There was 2 roots. If I may refer you back to the table, there were 2 roots there in a 1 by 1, and in that 2 by 2, etc. So that's very quickly, but I'm writing the numbers down like this. And when I rotated it like this, we got to that the numbers in front of me was, as a matter of fact, the so-called Pascal triangle. And I'm going to stop there and say, I want to show you something else now. Now, either you're going to see it or not. I'm going to show you an activity on our, call it our new homepage at the Limina Learner Management System. I don't know how many of you have managed to sign in there. I hope you have. There were 2-3 people now at the most who says they're not connected. So I'm not sure how this is going to work. If not, I'm going to open it from my computer. So I'm going to open an activity and a representation called falling balls. And I want to ask you, what has this got to do with this? So I want to connect. Again, I'm going to, for the moment, I'm going to say that going back here, in this thing here, I'm going to say that this is a typical mathematics challenge for geniuses only activity, where we say, can you see the pattern? Can you fill in the missing number? And I'm telling you that when we have just this raw contextless numbers like this, then somehow we're taught a certain pattern, to see a pattern here, and we grow up having learned this pattern. And I'm saying that this pattern in front of us, when it's out of context, guys, we're going to see that 1 and 3 is 4, and 3 and 3 is 6. Why would it be true? In the previous example, 7 and 8 and all that, there was not any of them was true. So if we're going to do this without a context, we absolutely do not know that that 6 and that 10 and that number we're going to get is correct, because somebody taught us a method to add them. It's absolutely not very good mathematics. What I'm going to do is to try create a context, which I must share with you was such an eye-opener for me a few years ago, that I really I couldn't believe that I never saw this before. And I'm doing this activity, this whole roots, because for those of us who's on the problem committee of the mathematics challenge, roots have suddenly become very popular as a question, and we've in this year twice made a mistake, in grade 4 and grade 5. It was very embarrassing for us. Our memo was wrong. We had to change it. So I'm trying to help that we get a better grip on this whole roots story. And so I'm now just for a moment, I want to see if I am going to open my browser. I'm going to open my browser. My browser is not open. Forgive me for a moment. Can I just check whether you can see that I'm opening Limina?
No, we're not seeing it. We're seeing your Excel.
I can't see. I'm going to stop share and see if I can share my screen or something. I must tell you that I find this difficult in all the media. I want to see what I can share. Okay, there's a screen. Okay, I can see if I can share
Let's take
this.
a break and then we can.
No, I'm now going past the break. Can you now maybe see it? Can I ask if
We're seeing it, you're right, we see it, yeah.
Okay, yes. So for everybody, I'm also showing you how to log in, etc. I opened the Limina Education Services. This is now our new homepage, MPS for Facilitators. There is also a mathematics problem solving course. That's the course that we want you to teach later on. You are facilitators. I'm now going here and let's get rid of this stuff. And it seems I'm in, and I'm going to the downloads folder, and I'm assuming you can still see. This is going to be, if I go to the previous page, then later on you are going to, there's the video recording is there, the assignment is there, the power, and we'll later on have the final assessment will be here. You will be able to do it in English and in Afrikaans. I'm going to open it just for the fun of it, just to make sure. You'll get 2 attempts to do it. It's going to open this afternoon, 3:01. It's going to stay open until midnight on next Sunday. You have 2.5 hours to complete it. And if you sign in, then it will appear here below. You'll get 20 multiple choice questions. Okay, we go out now, and I'm going to say, it's something like this. This is our structure, only this: welcome, download folder, and final assessment. You're going to be interested in the final assessment. I hope you're also interested in the downloads folder. I am going to do an activity. I'm going to some interactive activities. I'm going to open this executable file. You'll please tell me if it's working, otherwise I'm opening it from my computer. Here I go. Who like it? Erna, are we seeing something?
Not yet.
You don't see something like dots up here?
Yeah, you're saying you're downloading, but we can't see it opening yet. Says.
Okay. You don't see dots?
No,
Not yet.
It says open file.
Well, I opened the file.
Then it's probably on another page
Yeah.
of your browser.
Yeah. Okay. I'm gonna open it. So I'm now gonna open it. Sorry for this. It'll be best if I go. I'm gonna open it from my computer. It is open. Now I have to check if I can see it. Just a moment. I'm seeing it. Are you seeing it?
Yes.
Oh, now we're seeing it.
Dots. Okay, guys, what we have here is, that is why we turned it like this. What we have, we're gonna drop balls, an unending number of cases, we've got this strange number of dots arranged in this way: 1, then 2, then 3, then 4, all the way. I can choose. I'm not going to make it that long. I'm going to make it about that size, like that. I'm going to drop a ball there. What happens is the ball drops on this first dot, and then it has a 50-50 chance to go left or go right. So it'll hop to this side or hop to this side, and at any point it has a 50-50 chance to hop either way. I'm going to ask you, what has this got to do with what we're talking about? There I go. I hope I'm going. I'm starting. What the hell is going on here? Okay. Wow, one fell here in the left-hand side. Anybody wants to discuss? Anybody wants to discuss what is happening here?
It's a binomial distribution.
Yeah, it's a binomial distribution. Guys, I'm not going to go into. I'm not going into. I'm not at all going to go into probability or notation of notation for permutation and combination, all that thing. But what we have here is simply a representation of Pascal's triangle in this way. We could, for example, show Pascal, and so what the hell? Where does this come from? If I take it away again, so we've got dots and we've got numbers. So this is our big jump. Is to change from this representation to this representation and to ponder on what is going on here. It's very difficult to show. I thought I'll do better than this. After this, I'll go to Excel where we have our paths, our routes, and say, you see, here it is absolutely obvious, I hope to you, that it is. Can you see my cursor like this?
Yes.
From here, there's only one way to get to this. Let's write points. There's only one way to get to this point. There's only one way to get there. There's only one way to get to this left-hand point. But this first point in the middle here, there are two ways to get there, either from the left or from the right. And so this whole idea of adding is absolutely obvious. Well, I said when we do abstract Pascal's triangle, somehow we conjure up this formula that we're adding the two top numbers to give the next number. If you're working without the context, that's absolute nonsense. In this case, it's part of the structure. It's absolutely part of the structure. So if you are here at this, there are always two ways to get any point here, from the left and to the right. On the left, there's only one way to get there. To the left, there's only two ways to get there. So in total, there's 1 and 2 is 3 ways to get there. I think this is the idea. I hope you've got the idea. And so down here, what's happening down here is because you have you have a different kind of distribution here, and so the probability is very small that it will fall into this bin, then it will fall here into the middle, and therefore you will have this kind of distribution as illustrated here. So I think that was about enough. You have it available. You can just go to this site that I showed you, download it, and so you can use it for yourself. and you can use it for your children. And I think it's much more important to model this thing in front of us, than this root. But it's the same thing. Leon and all you guys, we had lots of trouble describing. It may go to the right, but not to the left. It can only go down, but may not go up. And you will notice that I took a shortcut. I just said the shortest route. The moment I said the shortest route, there was nothing of this not going up and not going across the same path a second time, etc. Here also, it's quite obvious what can happen. Balls cannot go upwards. Balls cannot go sideways. Are you with me? So all that nonsense about describing the routes, not going right, not going up, only be allowed to go left, only allowed to being right, that messed up both our grade 4 first round and our grade 5 second round questions and our memos. So there's only one way here, and that's down. But there are many different ways to get down. So let's return to, I'm going to close that. I think it'll be okay. I now want to go to roots like this. Okay, I'm with this data, I'm with this here, but I am going to take a shortcut. I'm going to say, I trust that I trust that this is okay with you, that just this first part from A to B, that was the shortest route. I trust that you understand that there was 2 ways to get there, 3 ways to get there, 3 ways to get there, 4 to get. You understand where this 4 and 6 and 4 comes from?
Yeah.
Okay. This was absolutely in this table here. We could take them one by one. They were all there. I described that path there. Absolutely. And so that describes to us from A to E there's only one way. From E to M there is only one way. From A to I is one way. From I to B is one way. So to get to this B, you have this, I think, I don't know how many ways now. So that is translated into this. I decided to just put this down. And so, again, I'm going to say this is control. I found Erna's write-up very interesting. She very quickly said that this is going to take too long. And so this is just too much work. So this is a classic situation of modeling where I was counting those stuff, but then I stopped counting and wrote down the numbers. But this was my database. So all those numbers that I wrote down in front of us, we are now just at this first question. All these numbers that I wrote down in front of us is true. I wrote them down. It's part of the database. And so now I'm looking for a pattern here. And there really is such an obvious pattern that this 4, if I can't show better, let me try again. I can't. I am in Excel, but I can't. Oh, this thing is in my way. Just a moment. I'm trying to draw. No, I can't write. No. That's all right. We'll have enough of a write-up, no problem. So this, as a matter of fact, we went from counting, systematic counting, to write down this structure, and from now on, I'm going to generalize this structure, and I have no problem generalizing this structure because it is structurally absolutely correct that this 2 comes from 1 plus 1. There's only one way to get to this 2, and that's from the left-hand side or the right-hand side. There's only one way to get to this right-hand, to the 4, is to come from the 3 or from the 1. There's only one way to reach that point. I could show that in, I think I've got many different other sketches here where we could show how this is working one by one, and that is what is happening here. I hope that we can now continue. That this, first of all, it's in the end, you understand that we went by physically counting the paths, we came to this situation. But now we have we can now say, we are not going to go on here from B to C, etc. I'm going to draw the paths as I did here in the beginning and get answers like that. We now have a model. If you like, our model is the Pascal triangle, and we are now going. So, for example, when I went from B to C, I didn't list anything. I trust that you understand my question was straight from B to C. And there I just made a new Pascal's triangle like that. That there is 1, and that is 1, 1, 1, 2, 1, 1, 3, 3, 1. And all I need is this C can only come from the left-hand side or the right-hand side. That's 6 and that is 4. I add them, it must be an add. You'll see now what's the problem. So there is the answer. There are 10 ways, 10 paths from B to C. And it is clear that with just from exactly that situation, I apply to this down here in exactly the same way. Well, anybody wants to comment on this now?
Yeah, this is a wonderful explanation of Pascal triangle.
Okay, you have to make peace with yourself. You have to get your teeth into this and tell yourself that there's only one way. You have to understand what is going on here. Okay, now how about another 5 minutes and then we're finished? I leave it there and now, yes, I have this 4th question. How many shortest routes are there from A to C via B? And so I had many people answering this, and I have 2 answers, namely from A to B there were 6 paths, from B to C there were 10 paths. Surely people like Leon, if I understood him correctly, was also good control, said not a damn, this is going to be too much work to do a Pascal's triangle, say all the way from A all the way to C would be just really too much work. Therefore, we rather want to use some theory here. And so now several people said 6 plus 10 is 60. I'm saying it's 6 times 10 is 60. So I'm going to ramble something and then we're going to take a break. For me to ramble, I think I tried to paste it over here. Yeah, okay. Question, guys. We have to think more fundamentally. So we actually have a very important principle called the fundamental counting principle. This, as a matter of fact, is written into the FET curriculum. And it's an absolute shame that it is in the FET curriculum and not in the grade 4 curriculum. It really says that if any event, doesn't matter what, like throwing a dice, can occur in M ways, like 6 ways, and another event like throwing a coin. That can be done in 2 ways. Then in total it's 6 times 2 ways, m times n. So I've just to connect to that, I've got an example of 3 cities. City A and B is connected by 4 roads, and B and C by 5 roads. How many routes are there from A to C? We first have to let it hang for a moment.
It's going to be 4 by...
It's typical, of course. This morning at 7:45, my pen was writing, and now nothing is writing. It's okay. Look, it's all about, if I'm going to say, I'm going to now be very much in a hurry. Let's say that is ABC. Then if the first row, the top road, if we call that A, and we call these roads, for example, 1 and
A, BC1, BC2, BC3, BC4.
Yeah, this road 1 and this road 2. Let me type something here. And this road 2 and 3. Then we'll have A1, A2, A3, A4. Did I say 5? It seems like 5. Okay. 1, 2, 3, 4, 5. From A, I can go A1, A2, A3, A4, A5. But I don't have to go A. I can go B. Then it would be B1, B2. So here is a question where we have multiplication, which is not so easily understood as repeated addition. And we simply have to extend our understanding of the repeated addition idea. So we've done several like this. We'll have A1, A2, A2, A3, and then after that we'll have B1, and after that we'll have enough. Probably I used some white background. Yes, okay. See, enough. We're going to have 5 here, 5 here, 5 here. And we're going to have 5 repeated. We're going to have 5 repeated 4 times. And somehow this repeated addition, namely this 5 and this 5 and this 5 and this 5, meaning 4 times 5. There are 4 ways from A to B and 5 ways from B to C. Now I trust that you understand that our problem here is exactly we had 6 ways from A to B and 10 ways from B to C. There are not 6 plus 10. I made a mistake there. Oh, I actually did it and then copied it. 6 plus 10 here should be 16, my mistake. And 6 times, I only had this one, then I added 6 plus 10. So many of you use 6 plus 10. 6 plus 10 would be 16, would be wrong. It's not that one followed by that one. It's 6 times 10. And I trust that this idea helps you. And in the end, it's about this serious, important thing. Likewise, it is like, I briefly say, surely, if we take this example, say Celeste has 10 blouses and 12 skirts, which you can wear in all different kinds of ways. So, for example, we can name her blouses 1 and 2 and 3 and 4, etc. And the skirts, we could call A. So with A and B and C and D. And I'm not going to do all she's got 12 of them. So with the first blouse, she can wear 12 skirts. So that's 12 outfits. With the second blouse, she can also wear exactly different skirts all the way, A, B, C, D, E, F, G, up to 12. So this repeated addition is sort of not so obvious. We have to do much more work that this situation will become a multiplicative situation, so that the answer is 6 times 10 here and not 6 plus 10 here. I assume that this is okay with you. Why not simply finish and then we say, now we take a nice break. Let's answer the last question. If we don't go via B, but all the way from A to C, how many different paths would there be? Well, the answer is you could simply from the top to the bottom construct a Pascal's triangle. It would go from there, and then I only need these middle ones to get to point C. C can only come from the left or the right. So you can actually work backwards. I trust that you all understand how I completed Pascal's triangle here, but only for those parts that I need. And I'm afraid it became quickly, Leon, very large, very much, but it wasn't necessary for me to write down the whole Pascal's triangle. I must know that that point C can only come from the left top one and the right top one. The left top one must be 70 because it comes from its left or right, 35 and 35. The 35 can only come from 15 and 20. The 15 from 5 and 10. 10 from 4 and 6. So we superimpose a super Pascal's triangle on that. And I know that we can now have permutations and combinations and have a notation for this, that where we can calculate the row 10 number 5, choose one, given 4, etc. But I'm not going to go there. I think it's absolutely not necessary in the primary school level. I think getting to this pattern is good enough. Well, I think so many of you communicated with me as quite like, I hope that you've got your teeth in it to some more, and afterwards even more. But I must say that I think that forget about formulas and notation and shortcuts. Here, getting to this pattern via falling balls will be a fantastic activity in itself. So simply getting to the situation where it was difficult to work with this, the moment we wrote it like this, it was easier for us to use our knowledge of this triangle, and so it really was all about actually I was planning to rotate this triangle like this. The moment we rotated it like this, it became much easier to work with the numbers, and we could extend that. So I hope you get your teeth into this. I hope you use the app that I'm sharing with you online, and I hope that you'll use it in class with your children, and that your children and you will be able to explain why there are 4 paths to get to B. And sorry, my mistake, 6 ways to get to B. And that comes from 3 plus 3. It simply has to be plus. Those 3 ways to get there and those 3 ways to get there gives you 6 ways to get to B. And so structurally, we can get to Pascal's triangle structurally, not inductively without the right to generalize it. The structure here is quite clear. I had all the right in the world to continue this pattern, and all the right in the world to continue this pattern, because I had a correct database and my structure said I could extend the pattern. Was that enough of a mouthful? A
Yeah,
quick
yeah.
comment. A quick comment from anybody?
How can you do now? Ising yami. Ising sila kaya inyan.
We are just anybody who got their teeth into this who wants to share an experience before we break.
I just want to say how expensive it is to learn to problem solve. It took me very long
Sure.
to just get to a point to do the spatial mapping. When I sort of saw the Pascal numbers, but to get that rotation thing in my head, that took long. And by the time I did that mistake of 6 plus 10 is 16, I just didn't have any more headspace. So I've learned something today, and it's because I wouldn't have doubted. You know, I just closed my working space was done.
Yeah, note that I'm thinking of sharing that. You guys may have heard of so-called taxi geometry, because if we go back to the this whole idea here, for example, if we worked with this thing, is very much the concept is very much of a city block, New York City. The streets are parallel with each other like this, and they form blocks like this, and a taxi doesn't go in between the lines, all along the lines. Those are roads. And so there's a whole theory there called taxi geometry. Erna sent me an article. And so Erna, both you and I are actually, I don't have good words to describe that. We are so used to this way of writing the triangle, but you would have noticed if you studied the article that they wrote it horizontal. Why can't you write 1 and 1 and 1 and 1 and 2 and 1? So in the whole article they worked with it in this way. It's just as obvious in this way. It's only us who can't recognize that as the same as this Pascal's triangle. So in another notation, it's straight this. Why not this? I only rotated it because I wanted to use the falling balls. The moment I had the falling balls, that motivated me to rotate it. But I didn't need the rotation in order to get these numbers here. I could, like in the article, we could have written it like this. Right through the article, they wrote it exactly like this. Why not? Why not write that like that? That's 1, and that's 4, and that's 6, and that's 4. That's enough. Shall we break for half an hour? It's been, 10:36. Okay, let's start again at 11. So we start at 11, then we have another hour, and then we break for lunch. Made the first one longest because we're still fresh. Shall we break? Oh, another comment? Mark, anything you want to share?
No, it took me a while, like Anna. It took many hours, and it was lovely grappling with it. But your comments were good because I used some combinatorics. So I just realized that there were only a certain number of rights or downs that one could have. And I just played with those combinations.
Yeah.
But when I went back, I noticed Pascal. So it was nice to look at it through fresh eyes.
Yeah. For me, the nicety of here is that I always had a nagging in my back of my head. Why the hell is it add? Why are we saying that 4 comes from 1 plus 3 gives me 4? I knew it, but I never understood why. So as a mathematician, I am a mathematician. You are also a mathematician. It was just unsatisfactory. It was like nagging, it was nagging. Guy sitting on my shoulder and nagging. Why is it add? I never understood why it was add until I understood this falling balls. The number of roots that follows is so obvious when you get your teeth into that. So I hope that's what you got. So, guys, problem solving is not a 5-minute thing. Okay? we must learn that. So note, I make one more remark that you guys just gave answers. That was a problem. Of course, there's a conflict. I'm going to ask you multiple choice questions, and then there's not just an answer. I realize that, but you must know that those are two totally different worlds. So to get to the answer might take you hours. So note that I don't really want to give you a restricted time, but you have 2.5 hours to complete the 20 questions. We give the children only 1 hour. So I think you can do great in 2.5 hours. We break, we start again at 11. Okay?
Thanks, Alvin.
Thanks, Tay.
Thanks.
Het dit gehelp, Leon?
Yes.
Afternoon, guys. I take it that you are seeing my T's. It suddenly feels... I actually checked. I thought, yeah, maybe I did it last week, but I don't find it. I always say one of the... a poor description of a teacher when a teacher says, where were we? So I hated to do something if I already did it, but it seems to me not so. So here is the question. Now I want to, I have now, for most part of the morning in the longest session, emphasized again, guys, we must, if we want to do something different, we must get away from number and calculation and answers. It showed you, I hope, time and again. Now, I showed at least 3 contexts in which, if we use number, we cannot explain. We do not see the structure. It's not possible. But the moment we use structure, it can say it's a different activity. I think we should, I'm not shooting down calculation, but let's just say it's something else, put it next to it. Like, I don't know, remember I'm not part of the system. In the old days, we had 3 question papers. A was speed and accuracy. B was about understanding, and C was word problems. Okay, and so you could have totally different objectives with papers. So you can have a calculation paper by all means, but we need also a problem-solving paper. So, right, now this is a typical geometrical problem. My point is that we should take care in not jumping straight into a number table and wanting to use number patterns when we can use the structure in the geometry, in the diagrams in front of us. So let's look at this, and so first of all, I'm gonna emphasize our control model. Namely, we've got a problem, what to do. And I say, I intentionally decide, will I do induction, will I do deduction? There's not much of a choice. If you do induction now, I trust you understand you must also do deduction. If I must find that, if I just do deduction, it's okay. I cannot do just induction because it doesn't prove anything. So I choose that I want to solve it by deduction. For the moment, I do not know yet how, but I'm going to say I'm going to use geometric reasoning, and then I trust you, I'm going to explain again what is recursion and what is a functional approach. And of course, our logic is there. The big plan is equivalent transformation. You replace one thing with another thing that's the same but different, but easier in the context. So deduction, geometry, both those two. Let's see what do I mean. And throughout I emphasize the Prost quote, the real voyage of discovering consists not in seeking new landscapes, but in having new eyes. Guys, you must work hard on an effort to get new eyes, because this is what it is all about. learning to think like a mathematician requires us to look with new eyes, different eyes. The moment you come and you say, yeah, you can already do that, you're okay. So what if you can do it? I know you can do it. I don't want you to do it in just one way. I want you to do it in 10 ways, so that you can understand immediately what the child is doing, etc. So yeah, I'm going to apply this as controls. This is my plan. I use this in all the problems that I do. I decide which of these I'm going to use. Okay, so let's go. How many dots will there be in T100? You know now already, if I say T100, I don't really mean T100. People do lots of multiplications, and then they each new problem is a brand new problem. You must always generalize. The mathematician always generalizes. So if you can solve T100, then afterwards I ask for T of 125, you must immediately know the answer. You're not going to do brand new work all over again. That's not how a mathematician works. So we're not really asking for the answer. I don't even give an answer like 5 and 6. Give the structural answer. Okay, here we go. Now, I'm going to start. I said induction, but make a plan. Let's try induction, investigate special cases, be systematic, organize our results, and now to carrying out the plan. I'm just emphasizing again that I'm going to say, I don't want to go here, because that is calculation or counting. We can work on that, but I prefer to say, for the moment, I'm again warning against bringing gimmicks in. For example, we all learn that there's a constant difference of, I'm not using it, there's a constant difference of 3, and that means the formula will be 3n something. Well, I can see that it's plus 1. So, but that's a gimmick that you know, but do your grade 4 children know it? You only know it after you have extensive experience of gradient and differences, etc. So that's not right. Okay, so I say control means I'm saying that's not easy. The answers hide the structure, even if we do get a formula. Why is that the formula? Rather use deduction. So I'm again going to say not that, but I'm going to do a functional and a recursive relationship. But I'm explicitly saying I'm not even going to try to do work inductively. So I'm describing my plan. I'm going to use a functional relationship through deduction. So here we go. With a functional relationship, I mean the relationship between the two sets. That's like the input set and the output set. And the formula that we're working with, what do you do to the 2 to get 7? You must do the same to the 3 to get 10. I've already given the formula. It's easy. I multiply by 3 and add 1. 1 times 3 is 3, plus 1 is 4. So for 100, it's going to be 100 times 3 is 300, plus 1 is 301. But that's not so easy. How can we do better than that? Just that. Now, I'm going to emphasize, so that's it. I'm going to emphasize just like I now said. What does this mean? It means, what do I do to the 2 to get 7? That means I focus on the 2 to think what operation I must perform on it. In this case, times 3 plus 1, to get the answer 7. If I now go geometrically, then I'm saying, guys, you must think the same way. I think we must think 4. We want 4s here so that we can use it with that 4. Just like, what do you do to the 2 to get 7? What do I do to the 4 to get this? Well, the moment you ask that, you put on these eyes, these lenses, and you say, let's find 4s. Well, if you look for it, you'll easily find it. I find them easily. I find 3 4s. Now, you see, why I say that we're using geometry is that all our children can discuss this. For example, I actually I'm contemplating of giving you a textbook examples and teacher's guide of this way we work with children. But I'm not working with children. I'm working with teachers and teacher educators. So the point is that in grade 4, for example, we say they have to describe. Can you describe the next sketch, T5? And can you describe, we are too much in a hurry to find a formula. Can you describe, say, the next pattern? If the next pattern is the 5th one, then all children can do this. I've seen them do it. I've worked with them. I know, and you know they can do it. They can. Let's take that away. How does the next one look? They can say, you look at it something like, the next one will be 5. I see 4 pieces, 5 to the left, 5 to the right, and 5 down at the bottom. Okay. What will the 100th one look like? The 100th one will be 100 blue ones on the left, 100 blue ones on the right, 100 blue ones on the bottom, and one in the middle, pink one in the middle. So I don't care if you say 100, 200, 300, and 1 is 301. You can say it in words, you can count, but if you can come with a formula, so much the better. But note that description is exactly the formula, 100 and 100 and 100. So let's come back here. For 4, I see 4, 4, and 4, and another 1. I see 3 4s and a 1. Now the point is, we do not want the calculation. We do not want the count. We do not want the answer. We want the structure. The structure, do not calculate. The structure is 3 4s, 3 times 4 plus 1. That's the structure that you can see in the 4th T without getting the answer. I hope you will now see what I mean with structure. Okay, now we must do exactly the same for 3 and 2 and 1. What does the same mean? It's actually difficult but very insightful. It means not there. In the 4th one I worked with 4s. In the 3rd one I'm going to work with 3s. I wanted to circle there. I see 3 and 3 and 3, just like I saw 4 and 4 and 4. Now I see 3. I can write it. 3 3s and 1. Do you see 3 3s and the pink 1? I write it like that. Now for the 2nd one, the same structure would mean I'm seeing 3 something, 3 1. I see 3 2s and a pink 1. I write it like that. 3 2s and a pink 1. Now really, I work from the biggest to the smallest, because for 4, what do you see? You could say you see 2 squared. You could say 1 less than 5. You could say double 2. You could, which one would it be? Well, you want to fit the structure. So what I mean with the same structure, I trust again, I'm going back to the 4. 3 4s, 3 3s, 3 2s. So you see 3 1s. I see 3 1s and a 1. We write it like that. 3 1s and a 1. Now I want you to understand that algebra, this is seeing the pattern in these expressions, T1, T2, T3, T4. Seeing the pattern means what's the same and what is different. If you ask the same question over here, it's not finding a pattern in 4, 7, 10, 13. The question is totally different. What pattern do you see? It's difficult to see it. Come guys, here. I've got 4 different expressions. What's the same and what's different in them? What we can now do is to study that structure, what varies and what remains constant, what doesn't change. It helps to remove the noise. So I'm thinking only of that 1, 2, 3, 4 changes. That's a variable. And that 1, 2, 3, 4 pink ones is a variable. But this 3 is a constant. 3, 3, 3, 3. The 1 is a constant, 1, 1, 1, 1. The plus is a constant, plus, 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 plus. The times doesn't change, times, 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 times. So, if I put it like this, in a table, then I only need this relationship between these 2 sets. There it is, there it is. So if we ask for 100, it's obvious. The pattern that we see is that it will be 3 times something plus 1. Everywhere, that is our ability to see what remains the same. What's the same everywhere? This ability to see this pattern is more important than seeing a so-called pattern in those numbers. You don't know why that is the number. Okay, so here we have it. So that relationship between the blue set and the pink set is so obvious, it's the same, that it's so obvious. If I ask for 100, that question mark will be 100. It's 3 times 100 plus 1. I said just now it's 301. I'm not even calculating the answer. You see, this thing is going to become algebra. This is going to become 3 times x plus 1. 3x plus 1. This is going to become algebra. Not that 4, 7, 10, 13. This is what we're generalizing. This is actually the method, not the answer. Those are answers. 4, 7, 10, 13 are answers. This 3 times 1 plus 1, 3 times 2 plus 1 is the structure. We are generalizing the structure so that, yeah, I didn't do it, but we could say the nth, for the nth term, it would be 3 times n plus 1. We are not generalizing number. Okay. Now, so I'm finished with that. 3 times n plus 1 as a matter of fact. So it's all about seeing that what is similar, the same, and what changes. That will empower us for algebra. Not being able to do long multiplication. Not saying we can see a pattern there. So what? This will become 3x plus 1, the algebra. Okay, remember we did this a functional relationship. Next, now I want to use a recursive relationship through deduction. The recursion, both in the table, is plus 3, plus 3, plus 3. Recursive is the relationship not between the sets, but between the elements of the set itself. From 4 to 7 is plus 3. From 7 to 10. That relationship is the recursive relationship. When we go geometrically, we must ask the question. If we start, I'm now going to start with 1 and go from small to big. Then we must understand, if we start with that thing, how do we go from the first t to the second t? I trust that you understand that we put an extra 1 on the left, an extra 1 on the right, and an extra 1 below. That's all. We're adding 3. From the second one to the third one, we're putting 1 extra blue dot left, 1 extra blue dot right, from 2 to 3. 1 extra blue dot at the bottom, from 2 to 3. 1 extra there, 1 extra right, 1 extra bottom, total of 3 extra, plus 3. And again, I add 1 on the left, 1 on the right, 1 below. But that means every time I must know the previous one. So the next one, I know I put another extra 1 on the left, extra 1 on the right, extra 1 below. Now let's write that. I already wrote down the first one is 4. The next one I'm saying is 4 plus that 3. Do not say it is 7. We do not want to calculate. We want to make structure. We're very clever in doing this, so do not give the answer. It's 4 plus 3. Withhold closure. So this is just indicated division without the answer. It tells us structure. So if we do the next one, we do use the structure. The next one, we add another 3. Do not calculate and get the answer, because this is showing us the structure. Not calculate the answers. Study the structure in the formula. The next one, we add another 3. So from this 4 in T1, We add 3, then 3, another 3, another 3, another 3. So that's exactly what we wrote. Why do you want to do something else? Why the moment you get 4 plus 3, you want to say it's 7? You must try to withhold closure, to tell yourself you're not going to calculate. Because if you don't calculate, you're going to reap the benefits. What's the benefits? Let's now impose structure. We all know that that's a long way. 4 plus 3 plus 3 plus 3 is a long way. Let's make it shorter. It's 3 times 3. There are 3 3s. That immediately means there are 2 3s. That immediately means there's 1 3. We wouldn't normally write 1 3 there. We'd just write 3. But because I'm unpacking structure, I write the 1 times to make it very clear what's the structure. Even worse, even better, even more fantastic. The 4, I'm going to write the 4 as 4 times 0. Why? Simply because I'm working from bottom up. If that was like 3, 2, 1, then I expect that pattern to continue like that. So I'm working with that structure. I think I'll just go out and then I'll have to just redo that. No problem. Quick. Like that. So that's so we're the same as just now. We ask now, not what's the answer. The answer is 4, 7, 10, 13. There. We don't want that. We want to study the structure. Again, we impose structure by making the structure visible. We look what is the same, what changes, and again, it's quite clear. It should be quite clear that we have exactly the same structure 4 times in each one of them. It's 4 plus everywhere. 4 plus, 4 plus, 4 plus. It's times 3, times 3, times 3, times 3. It doesn't change. What changes is the 0, 0, 2, 3, 1, 2, 3, 4. So the blue set and the pink set, they are the variables, and the other stuff are the constants. And so our ability to now see what's the same and different here, how to generalize. And so if we ask, what about the 100th T? We know it will be 4 times something plus 3. 4 times what? Well, now we have to, I'm not sure what I wrote on the slide, so let me write and saying we're looking for this relationship from there to there between the blue. What do we do to the 2 to get 1? What do we do to the 4 to get 3? That's all that we are asking. If I do that, I must again discard it. I could keep it, but I'll just go quickly. Okay, so if we now ask for 100, we're looking for this horizontal relationship. It's clear that that is the relation to 1, 0, 2, 1, 3, 2. I should have written it here. 4, 3 is 1 less. So 1 less than 100 is 99. So the answer is 4 plus 99 times 3. I'm not calculating the answer. That's the structural answer. And that will become algebra in grade 7 and in grade 8. 3x plus 4. 4 plus x times 3. That will be the algebra. So looking back, we could work on that. Those two answers are exactly the same. So I thought I had another slide.
Oh boy.
The answer I gave there is exactly the same as the previous answer. 3 times 100 plus 1 and 4 times 99 plus 3. That's the recursion. That one's the function. So we have two different equivalent formulas. I trust you understand how we're getting there. And that you will be able to do similarly in any such activities. And I'm working on us working with children on the day of the final to help children to think exactly like this. This will make them great in mathematics and algebra, not long multiplication. This is what I wanted to do with T. I decided beforehand I want to do it in two ways. This was the one way. We call it recursive. It gave me this kind of formula. Before that, if I go quick, back, then the other way was to have this formula, which was the functional formula. So they are different, but the same. Very important. Okay, I stop for a moment and ask if anybody wants to make an input, ask a question, tell us of a better way. Or a different way. Well, let me ask a question and you answer it, and then we can discuss. So, do you think grade 4s can do this problem?
Yes, especially the geometric approach.
Yes, I want you to convince. I'm trying to convince you, and I want you to convince yourself that this numeric approach is not the way to go. It undermines our approach to algebra. It is a straw man of algebra. This structure, as here and in the other, remember there are these two approaches, is much more aligned to what we mean with algebra. Okay?
You see,
So,
grade 4 learners, they prefer using this, the common difference, 4 plus
yes,
3,
yeah,
7 plus
Stephen,
3.
it's because you teach them to them.
Okay.
Stop teaching it to them. Ask them, let them discuss. Let them discuss what do they see. Give them this pattern as is. Give them this pattern and say, discuss. What do you see? Can you sketch the fifth pattern? Note, I think we can sketch the fifth pattern. Then can you describe the 100th pattern? Not one of us is crazy enough to try to sketch the 100th pattern. It's in your head. Surely everybody sees the pattern. So the 100th pattern will be 100 on the left, blue, 100 on the right, 100 on the bottom. So children will say, I see 100 and 100 and 100 and a 1. That is nirvana. That is heaven. That is as close to algebra as you want to get. Don't fool yourself because you taught them or they were taught somewhere else by the parents or their older brother. Here's a shortcut. Here's an easy way to do it. We must have long-term goals in sight and not short-term, quick tricks to get the answer now. What do they do next year? Come on, guys, this common difference stuff, to my mind, is like, there's no use doing common difference without studying the straight line, which has a constant gradient. And that constant difference is the constant gradient if you have a difference of 1 at the top. So plus 1, top plus 1, plus 1, plus 1, the bottom plus 3, plus 3, plus 3. That 1 over 3 will become the gradient of the straight line. When we get to the straight line and the formula for the straight line, and the gradient of a straight line and the y-intercept of a straight line, then by all means we are ready. But why on earth we forever try to take like grade 9 work and try to pass it down and down and down, and now suddenly we're very clever in grade 4. Of course they can mimic. They can mimic it. They can, is there another word for mimic? But understand is something else. I think you first need lots of work for understanding, not even common difference. First, just multiples. How do they know what's the formula for a multiple? How do they get there? We do tables. Why don't we do multiples? And when we do multiples, we can do common differences. So the multiples of 3, 3, 6, 9 is a common difference of 3. The multiples of 5, 5, 10, 15, 20, 25 is a common difference of 5. If we start there and work slowly and apply that knowledge, like what's the 100th multiple of 5? And we understand that that's 100 times 5, blah, blah, blah. Lots of exposure to multiples, common differences, also when it's not a multiple. Why not put on a like 4, 7, 10, 13? I would much rather see us that numbers, all of them leave a remainder of 1 when you divide by 3. So I'm saying, for example, that 4, 7, 10, 13 is actually difficult, but 3, 6, 9, 12 is easy. 3, 6, 9, 12 are multiples of 3. But what are these? These are all 1 more than a multiple of 3. But now we're in the pound seats. 1 more than a multiple of 3. Again, rephrased, it means that if you divide by 3, the remainder is 1. All these numbers, 4, 7, 10, 13, leave a remainder of 1 when I divide by 3. 4 divided by 3 is 1, remainder 1. 10 divided by 3 is 3, remainder 1. 13 divided by 3 is 4, remainder 1. Now that remainder 1 is the same for all of them. We need lots of work throughout grade 4, 5 and 6 and even grade 7 before we come with this gimmick of a constant difference. I'm pushing that we understand structure. Okay, Stephen, we're still friends?
So we're still friends, then I will be friends until.
Okay, good. Let me see. Okay. Any other comment and input? Did you agree that the grade 4s can do it? And they can do it structurally. That means we must teach them. Much of this, something like a functional relationship and a recursive relationship, or actually social knowledge. In other words, you teach it to them, you show it to them. But it stops after that. You cannot think for the children. They must do their own thinking. But when it comes to words and relationship, words and notation and convention, you first multiply before you add. They cannot discover it. No matter how clever they are, we must tell it to them. Forget all this nonsense about not telling them. We tell them. But we do not try and tell them conceptual knowledge. They must have conceptual knowledge like place value in themselves, in their heads. It's not even teachable. Okay. Well, if nobody's going to comment, then up to 12. I'm doing one more of these. I call these designs. And again, we should be studying all kinds of patterns here. And it is about the geometrical relationships. And I ask in design 83, and I ask actually many questions. I ask how many orange tiles are there in the design. But if I say design 83, I don't really mean 83. I mean 100, 120, 76, 124,000, 5,023. So the art of mathematics in generalizing is, if you can really answer it for design 83, then you will answer the structure, not the numerical answer. If you get the numerical answer, then for each one that I said, 75, 100, 123, 4,520, each one of them will be a brand new problem that you have to start from the beginning. And that a mathematician is lazy. We don't think like that. So how many orange tiles? How many red tiles? How many gray tiles? How many tiles altogether? So we must put on our lenses. So very quickly, I'm going to say gray tiles. I let it hang. There. Can you describe in design 83? Well, can you describe then, before I take my shortcut, let me ask you, can you describe how design 5 will look, the next one? And can you describe in words how design 83 will look? Who wants to give it a go? Who wants to give it a go? Come, it's very important. It empowers you. If you can explain it to yourself, you understand it better. This, what do you see? Can you please describe how design 83 will look? And how do you know that? Come, who's my volunteer? Who wants to take a go and describe to us what design 83 will look like?
I'm going to take a risk. I'm going to get shot down. It's Lee.
Okay, Lee, we're listening. Everybody listens. Is he explaining good enough for us to understand? And is he correct? And is it a good method or explanation that we can immediately use? Okay, but now it's part of the culture. We're listening.
Right. So in the red tiles are always the rows are equivalent to the number of the design.
Yeah.
And the columns are one more than the design. So in 83, there would be 83 rows and 84 columns.
You're with the red ones.
Yeah. Now, if I was going to do the yellow ones, each time there are twice as many on the row and twice as many on the columns. So with 83, it would be 2 times the 83.
Okay, now listen. Yeah. Okay, now tell me then, how will you calculate? Let's go for the total number of tiles. The total number of tiles in the 83rd design. How will you calculate it? Tell us.
6. I'm just thinking. It looks like each time the rows, it's 2 more on the thing. So if it's 83, it would be 85 by 86.
Yeah. Okay. I trust everybody listens and followed her. Sorry, let us see. We can't hear that well. Say again. Who's speaking? I can't see.
Can I try, Alwyn?
Manari. I can't see, but I can hear. Yes.
Thank you very much. Design, I will need some help with colors, please. Design 83 will have a square a rectangle that is 83 by 84 of red tiles.
Yeah.
And then it will have 4 by 5 4 plus 5, all of that by 2 number of yellow tiles, and only 4 grey tiles that will be at the corner.
Yeah. Okay, I followed. I want to stress this idea of a variable, and this again starting with 4. And so first of all, I'm going to answer the question as I put it. The grey tiles, of course, the answer is there's 4 grey tiles, no matter which design it is. Do we all agree? There's 4, there's 4. Why? The grey tiles are the 4 corners. So all of the designs have 4 grey tiles. That is a constant. It doesn't change as the design changes from 1 to 2 to 3 to 4 to 83. It's always 4. That was great. Now, I thought that the red ones was also a walkover because we did it last week. May I remind you? This last week I said, do not. Okay, I'll do it quickly. We said last week. I should actually just see if I can use my pen. We said last week, do not say it is 2 and 1, 2, 3, 4, and this is 6, and this is 12, and this is 20, and there you stop. So what if you say that? What's the 83rd one? You understand? What's the 83rd? What's the 83rd one? Picture 83. What's it? I'm saying again that this numbers does not help at all. So, sorry guys, last week, this was the first one where I tried to convince you about structure and not answers. Those are answers. Structure is to say that you see 1 times 2. Structure is to see that you see 2, 2, 2. You see either 2 3s or 3 2s. Here you see 3 times 4. I see 3, 3, 3, 3 or 4, 4, 4. 3 4s or 4 3s. The 20, how did I know it's 20? Come on, I saw the 4, you saw the 4. So you see 4 times 5. Now this is the structure that we can. There is absolutely no problem that because if that is 4, it's 4 times 5. If that is 3, it's 3 times 4. If that is 83, the answer would be 83 times 84. Would you agree with me?
Yes.
We did this structure last week. All right? And so I very quickly said, there it is. This is what structure is about. This 2, 6, 12, 20 answers is now much more difficult than this constant difference of 3. Because here the difference is plus 4, plus 6, plus 8. It's a quadratic, etc., etc. This example of where the answers prevent us from even finding some pattern at all, not the functional. So I trust that this was okay with you. And if I take this, if I ask PowerPoint to please give me back my cursor. Doesn't want to. Then I just want to get out here for a moment. Sorry, escape doesn't help people. Just for a moment, I am stuck here. Okay, then I'm going to stay there. No, I can't. Damn it.
Alwyn?
Yes.
Control Alt and delete twice.
What?
Control Alt and delete twice. and end the task.
Okay, task manager.
End the task.
Ending the task will remove everything.
Yeah, I still have I still have my pen here. I don't want to put off my damn computer. Okay, let me work. Let me, and I'm not. Oh, here. I'm just gonna try and go out of it like this, and then I'll go in again. Okay, we still have the problem. Sorry, this is one of the no-nos of finding out how that works while you're presenting. But really, I can only try to start a new presentation. Everything is ready and waiting for us, but I can't get out of this mode.
Alwyn, as jy bo op jou uitveer klik?
Undo or redo, something like that.
Of op die, klik eers op jou pyltjie heel links bo.
Ja, maar ek het my potlood, dus ek het nie my cursor nie, sien jy, ek skryf.
Ja.
So I can't get rid of my pencil. So when I go to my here I can see. So I'm gonna stop sharing, go out. If I can't close it, I'll minimize it. Then I'll maximize it. Okay, then I'm gonna try there I'm okay, nearly there. Okay, at last I am here. Now, if you don't mind, is this okay with you guys? Let me just finish this and then we're gonna break for lunch. So we already answered the question for orange, and I say we can do a function or a recursion. So I'm not doing at the moment the gray or the red. That's done. We did the red last week. Let's concentrate now on the orange. Now this is where you say, what do you see? Well, obviously we must see at the bottom and at the top is the same, and the left and the right is the same. And so when you think structure, then you must think 4. And when you say the bottom, in the bottom there's 5, then the moment you say 5, you're in trouble, because you should be thinking in terms of 4. So it is true. I could say, I actually don't want to use this damn pen again. Okay, I'll use the pen. Shall I chance it? I could say that it is 2 times 4, the orange, because I have 4 over there and I have 4 over there. And I could say plus 2 times 5, because I've got 5 at the bottom and 5 on top. But if we're going to start generalizing this, then I would have to say the number of orange tiles for the fourth one is 2 times 4 plus 2 times 5. Would you agree with that? It would be okay. It would be okay. That would generalize into 2 times n plus 2 times n plus 1. Then I must think in terms of variables. This 4 must just now be 3 and then 2 and then 1. And there's no place for 5. 5 I must think also in terms of 4. So I'm removing the pen and I'm maximizing it. And if you don't mind, I'm going to say finish with the gray, finish with the red, go for the orange. In a function approach, I'm going to do it like this. If I look at the 4, then I want to find 4s. Then I say there's a 4 on the side and a 4 on the other side. And this 5 is actually 4 and 1. So I do mean that my lines are equal. This line is a 4, so I see 4 4s and 2 1s. I'm writing it like this: 4 4s and 2 1s. Guys, it would not be a problem if you wanted to work with 5, but it would just be more work. Let me say that first, rush through and then maybe come back. So that 2 is because there's one more at the bottom than on the side. There's 1 2 3 4 on the side and 5 at the bottom. 5 at the bottom, 5 at the top. So I can describe the 83rd one by saying orange, 84 at the top, 84 at the bottom, 83 at the left, 83 at the right. I trust. Is that okay, Manari? Hello?
Yes, Alvin, that is what was going on in my mind. But
yes.
I said a different thing.
Yeah, but I was pushing a bit to go a bit faster, and instead of saying 5 to say 4 and 1, because the moment I said 4 and 1, instead of 2 4s, I could have 4 4s. And everywhere I could have the same structure. There's a 3, there's a 3, there's a 3, there's a 3, and 2 1s. So for 3, I can say 4 times 3 plus 2. Here is a 2 and a 3. In exactly the same way, I just this morning decided to keep all this red stuff to emphasize what I mean with the same structure. The one is just bigger than the other. So you go from 1 to 2 to 3 to 4, and the structure is exactly the same. Namely, everywhere is a 4, everywhere is a times, everywhere is a 2. So those are constants, and so this is the variables that change. Okay. We again, if you wanted to, if I take a red pen, take my pencil, you could have said, you see, for the orange now, you see 2 4s and 2 5s. Would we agree? But you see, you would never leave it like that, because then, of course, the answer for the 83 would then be 2 times 83 plus 2 times 84. But that would be unsimplified algebra. If we generalize this, then we would maybe have said that if this number is n, then this number would have to be 1 more, n plus 1. So you see, you sort of have a complicated Yeah, you are saying that you would say that the formula is plus 2 times n plus 1, which I assume you see a mile off is the same as my 4n plus 2. I'm saying this, if this is n, this formula becomes 4n plus 2. So we have these two formulas. We always have many different possibilities. Can I just rub in that the essence of this is not to think this 5 is not just a number. It's not just a number. It's like our 16 was not just a number, it was a square. Our 6 was not just a number, it was a multiple of 3. Our 25 was not just a number, it's a square. And so this 5 in the fourth picture, you must think of it in terms of 4. So what I was really saying was that 5 is 4 plus 1. I see 5 and I say it's 4 plus 1. I hope you follow this little PC. If I now rush to, I'm finished. I have got this formula, 4n plus 2. Or Minari's formula is 2n plus 2 times n plus 1. If I now go for recursion, then I would see the recursion like, yeah, I could just say, what does this mean? It means if n is 1, then we get 6, and 2, then I get 10, 3, I get 14. Of course, I get that. So I could check this formula against the table and help me with the formula, but it's neither here nor there. So recursion is the other way. We've always got two ways to work. When I work with recursion, I take it away again. Please watch the sketches. What recursion means, it just means how do I go from 1 to 2 to 3 to 4. So I look and I see, next, I see here on the side I have 1, next. Why did that happen? Nearly there. I'm finished there, we are here, finished there. Now, only now I'm with recursion. Then I say, look, this is 1, and this is 2, and this is 3, and this is 4. So the way we go from design 1 to design 2 is to put in an extra orange one on the side, and on the other side, and on the top, and at the bottom. Would you agree with that? The way we go from the one to the next is for orange. We're at orange. For orange is the first one had 1 orange on the side and 2 on the side. 2 on the side and 3 on the side. 3 on the side and 4 on the side. 4 and 5. And that means basically concretely, geometrically, going from design 1 to design 2 means I add an extra orange tile on the left side, and an extra orange tile on the right side, and an extra orange tile on top, and an extra one at the bottom. That becomes 2, 3, 4, 5. 1, 2, 3, 4. So now we go to numbers. The first one, how many orange tiles are there in the first sketch? There is 6. I count them, 2, 4, 5, 6. But in the second one, there are 6 plus 4, right? But you must see that I'm now doing this exactly like I did the T's. So for us to, and the children to learn mathematics is not to think that each one of these are new. I'm using exactly the same thinking that I used with T's. And I'm using exactly the same thinking that I used with a red rectangle. So here I go, do not calculate. For the next one, I add another 4, one at the left, one at the right, one at the bottom. And then we give structure. We say that's 3 4s, 2 4s, 1 4, 0 4, just to give structure. This makes us clever, not little patterns. Seeing this, what's the same in this? So we must understand what's the same and what is different. 6 is the same for all of them. Plus is the same. Multiply is the same. 4 is the same. It's only the blue ones and the red ones that change. The pink ones, they are the variables. So if you want to have for 83, it will be 82. I hope that's obvious. 4, 3, 3, 2, 2, 1, 1, 0. That relationship between the sets. If you ask for 25, if that's a 25, this is 1 less, is 24. In general, if this is the nth pattern, then this will be n minus 1 times 4. And therefore, again, you have these two different formulas. The structure, the function one gave me 4 times n plus 2. The recursion one gives me 6 times n minus 1 times 4. They are equivalent calculation plans. They are different methods giving the same answer. And you know how important it is in algebra to show that those two are the same. As I showed just now that Minari's formula was the same as my formula when we start simplifying it and replacing it with equivalent. But the emphasis here is on this. This is the structure. This 4 times something plus 2. This 6 plus something times 4. A constant of 4. A constant of 6. A variable of 0, 1, 2, 3. That is the algebra. And I say, if you understand this approach, then I'm absolutely sure that if we understand structure, we can look at this fourth design and say, how does the 100th one look? The 100th one for orange tiles, well, the 100th one in total will have 4 grey tiles, and the 100 times 101 red tiles. How many orange tiles? 100 on the left, 100 on the right, 101 on top, 101 at the bottom. Not so? Now that's structure. Nowhere was I interested in saying the answer for the 83rd one. I didn't want to answer 4 times 83 plus 2. I don't care what's the answer. I want the 4 times n plus 2. May I say, and that is structure. And if I follow structure, then my what says it's time. So guys, is there a quick comment, question, remark, worry, enthusiasm, alternatives that you'd like to throw in to share with us? Because I didn't think for what I tried to get you to think like I think, but I don't believe it. I think you have your own way of thinking. But what I don't want is to say, you've got a method, you get the answer and you're finished. I mean, then you're wasting your time. You're absolutely wasting your time. So who wanted to speak? Quick.
Alwyn?
Yes. Please
Alwyn?
speak.
Yes.
Yes, Manari.
Okay. My observation from last week, the things that you have been encouraging are actually things that are not really the focus in terms of teaching more often, in the sense that the structure that we find in the properties of operations, the structure that we find in geometric figures such as the one that we've been exploring, are seldom the focus of discussion in the teaching of mathematics.
Well,
And,
then they're not
for
following.
me-
They're not following caps. It is Nico can come in. It's in caps. It is in, for example, you know, the Sazzle and Zalo textbooks that we wrote. So I will. Sorry, it can't be true because I wrote the pattern stuff in from grade 4 to 6, and this is exactly what is in the grade 4 to 6 books.
Yes, but Alwyn, yes, it's in the curriculum. Yes, it's there in some books, but the rationale behind those tasks in the books isn't there in many. The issue here is
Isn't
one
there in
answer.
many? Isn't there in many what?
The rationale
Is
behind the
not in
tasks given, and
Yeah.
teachers, and not only teachers, most people who are interested in the work of teaching do not actually look into that as things that are the building blocks for
Yes,
sense making.
well, this is why we are here. We are here to go out as disciples and to try to convince them. And so I'm saying that we can make the case that it is in the curriculum, and it is in the textbooks, and it is in the teacher's guide. And then probably after lunch, I think I will then just show you some examples of what is in the children's books, and they are being used. And therefore, what I see as our task here of facilitators is for us to go out and have workshops and to engage teachers on these ideas, because this is what, remember, we want to teach something differently that will make a difference. Because if we teach the same, the result is the same. We do not want the same results. Thank you very much. Sorry, Manari, but you know, we do understand each other. It's difficult to change. So it's difficult for me and for you to change. So for the classroom teacher, not taking anything away from the classroom teacher, but he may have not have had exposure. Remember, the course started off last week with saying we are all a product of our own previous education. And many of this kind of stuff, when we're used to calculations, is foreign to us. It's not what we thought is mathematics. So it's a heavy thing to go in with this under our arm when we work with teachers. I understand that.
Alwyn?
Just speak.
Hello, Nico, yeah. You mentioned my name. I think I want to understand both sides. I think from where you are coming from, Alwyn, and getting the facilitators to think about, to do things in a certain way, I think it's highlighting and it's adding value. At the same time, I think Manari is looking at it from the perspective of what's happening in our schools currently. And I think there has to be a medium, you know, kind of a middle ground. If you go too much on structure at this stage, then we may lose our teachers. We may ease into the structure and get them, because as you say, I mean, you just mentioned it, it's a product of our experiences and our learning. So if you're going to go into a different approach straight away, you know, you must take what they know already and build on that. So I think
we must give them. We must give them different experiences.
Absolutely.
Sorry, I do not agree. I'm one who actually believe that there is no such thing as evolution. It's a revolution. If you do not come with a revolution, if you can't change this halfway. You cannot have problems Friday afternoon. Problems solving is right across the curriculum. This is the focus right across. The moment you come with implementing it halfway, then you undermine what you want to achieve. You know, so I've said it from many platforms. I'm a revolution man, not an evolution man. I said it in 1992 when we had that international political dimensions in mathematics education in Broederstroom. I put it up front there. No evolution if you want to work with methods. A revolution, in other words, a radical change, not a little bit by little bit change.
Thank you, Alvin. May I contribute?
Stay, by all means.
Yes. Yeah. No, thank you. I think, as colleagues have just said, you know, this is really challenging. I think most of us who are really driven by this curriculum coverage and so on in schools, we end up being trapped, in the vicious cycle. And I think we don't give teachers what we call it experiences. That's the unfortunate part, I think, when we engage with them. But furthermore, I think what was Nico saying, that maybe time with us is that we delay this and then try to now do what? To like even now the country is like we have different education systems because different provinces, you'll find that the focus maybe in some instances is only on high school educators. We are doing what is called maybe pressure cooking or firefighting there up there. But if this can be done, I think that as we are here, most of us are involved in South African challenge, and we are saying, let us expose our teachers from junior grades to this. And I believe from junior grades, if this could be the approach, because really it's really sinful for me at junior grades to teach products, because that's what we are doing, unfortunately, the 1+2, and we don't have a structure. We don't even try to create a context. We are just happy that a learner can add 1+2. So I think I'm appreciating this. It's also challenging the way, really, I think, but I think that's why we lost the focal point of teaching mathematics. I think we rather be late than never. We'll try our level best, but I so wish there could be a platform beyond this one, whereby really we can challenge and try to penetrate the entire teaching of mathematics in the country now, because this is really, I think this is a focal point of teaching maths, rather than what we are busy doing and chasing syllabus and so on in the mainstream. Thank you.
Okay. Anybody else?
Alwyn, I just want to take up on Stay.
Okay, Erna.
If they can invite us to their classrooms where they do this with children, so that we can take video and show the teachers the children can do it, then we can spread the message.
Yeah, but I think you see, there's no need for us to really be talking about whether learners are capable of learning. Definitely learners are. But I think the important thing here is, like one said, teachers need the experience. Teachers need to engage in this kind of programs in ways that we are seeing and experiencing them now, for them to have confidence to engage learners in the same way. There's no way that we can say, teachers go do this, when teachers are not confident in actually engaging with this kind of content or with this kind of processes. I think that is what we should actually focus on, getting teachers to be comfortable with this than anything else.
Change is difficult. Change is always difficult. And teachers find it difficult to change. We simply have to try to give them other experiences. If our own understanding is dependent on our previous learning, then let's have some new learning. Let's develop and share and discuss some new experiences instead of being so confident with the old ways. It's difficult to adapt to new ways, but you have to. It depends on how hard you try to remember. Let me formulate it this way. We say it's difficult to get rid of bad habits, but it's just as difficult to make good habits part and parcel of your automatic system.
Alvin,
So you have to practice to make it good habits of mind. you can't do it with one little problem or two problems. You must, to become a habit, you have to repeat it and work on it.
Alwyn, yeah.
Yep.
Alwyn, I just want to add something. I'll give you an example. I mean, the focus, you know, it is actually very sad. The focus is on number, not number as in mathematics, but the number attending a class, the number here and the number there, and who's doing this. But the focus is not on what is actually happening within the classroom. I mean, last night I just did a report and submitted to my director. And I asked her, I said, but you know, this is talking about numbers, how many learners attended the winter school, and what, you know, whether there was social distancing and all of those issues. I said, but nothing was about what was done in the classroom. What kind of mathematics did they do? What kind of science did they do? So the whole thing is about number and not focusing on what's happening in the classroom. And I think we need to change that. If we need to get our teachers to do this, we need to change what's happening in the classroom. Thank you.
Yeah. We must understand, guys, we are not teachers. We are change agents. And I can say, I selected you to be a carrier, to be a messenger of this message. And that's not an easy task. I can share with you later on how I see the role of the change agents. We are change agents. We try to help teachers to change, but we also need to support teachers. You cannot come there and say, do this, and when you go, then they leave it again. You have to come again, and there will be reasons why they're not doing it. And you have to try to help them to solve it. So for you to be a change agent means that you must fulfill different kinds of roles and influences on teachers to help them to change. Therefore, so that our children can change. Okay. Right, guys, that's good. Let's break for an hour. And when we come back, I'm quite open for anything you want to discuss in an hour at 13:20. And then, if I understand it correctly, we will work for another short while. Make sure you're comfortable with the learner management system, and not much more. I think we can end early. I don't want to put too much more on the table. Shall we break for an hour? It's heavy stuff. Okay?
Yes, Alvin, thank you.
Thank you.
Yes, you can start, Alvin.
Okay, afternoon, everybody. We don't intend to stay long. About planning, I will just say that we'll have to see, how it goes with COVID, and we hope that final is on the 28th of July. And you will remember that the invitation, you all indicated that you would be available to work a little bit with teachers and children. So just give in the next week or so, give Patrick and myself a chance to see what is organized, who's available, and we'll make a little program. I'm not going to be prescriptive. First of all, again, I repeat, I would very much like our facilitators to present. Guys, there's nothing as good for understanding as presenting something yourself. So that will be our first one. On that day of the 28th, teachers bring the clever children to the venue. We can have a little session with the children, and we can have a little session with the teachers. We do not advise to take them together. We thought so last time, but it really didn't work. So I will prepare a suggested activity. I think the two that I think I will propose, but I'm not prescriptive, that we do, and I'm not saying how we do it, is a little geometric pattern activity and a fundamental counting principle. This systematic, it must be about systematically counting something, not triangles this time, but something like outfits as we had earlier today, the tops and the bottoms. How do you combine them? The whole idea of multiplication is not so obvious to our children, and we must develop that idea. So the heuristics of trying special cases, being systematic, organizing your result, looking for a pattern is a must that we do that with children. You all, and teachers, you all understand that if you're just used to doing long multiplication, those things are not on your radar. And so it's very easy, few ideas that we want to do with our teachers and with our children. And that will then be, our first feeling for this year. And then we will see how it goes. We would like, there's money to have workshops in each province towards the later in the year and early in next year. And the whole idea is to improve participation and performance in the mathematical challenge. Is that okay, Patrick?
That is accurate, Alwyn.
Yes. Let us just see how it is going, and how we must work with AMESA to organize venues and invigilators. You guys are not invigilators. You are facilitators. And we'll ask regions and provinces to organize teachers to invigilate, while we will do the workshop stuff. All right. I just want to show three little things, but before I even do that, if necessary, I'd rather say if there are any organizational or misunderstanding of structures or whatever, if you want to discuss something broader about objectives and timelines and whatever, speak now. Audrey?
Oh, sorry Alwyn, ek was besig op my foon, het my nou uitgevang.
Yeah. Is there any questions that everybody wants to ask now about, organization, structuring, where are we going, how are we getting there, whatever. If we can answer it, if you feel better, we can try and answer it now, or we pass.
Alwyn?
Yes.
One of the venues used last year was the WITS education faculty. Is that going to be one again?
Well, Patrick will know better.
Okay.
We have to find out how many people, we have. Also, I know about his last email, Patrick said that full COVID restrictions and stuff will be at play. So we must look at how many people are writing. We're just finishing that now. And so we must see if we can get a fit between venues and participants. We must have a big enough venue for the numbers. And we will still follow up. It's really a problem that some of our smaller provinces don't really have many participants in the third round. So there's one or two. Now, you don't want to do a workshop with one or two learners,
Yes.
So we really want to try to make it work. So if there's just a handful, then even if it's just 5, we do our thing, because it's not just to see who are the winners. We have a role to play. We feel we have a responsibility to develop and support teachers and children. So it's not just about finding the best 400 learners in the country. We must invest in developing. That is what this project is all about. Okay? So the fine print, we must still see what we have.
Alwyn?
Yes.
Alwyn? Nico, yeah. I'm just checking with the fact that we may go on to level 5, the president's announcements tomorrow.
Yeah.
Will that affect, how will that affect round 3?
Yeah, I must tell you, I don't know. But I know for sure that if they say schools are closed that time, I don't think we can go ahead. Yeah. We will have to postpone or leave. You know, I don't know what Patrick says.
No, I would suggest, Alwyn, that maybe we played by ear. You know, last year, round 3 of the challenge was compromised. We didn't have it. But we had the round 3 of the SAMO, both the junior and the senior SAMO.
Yeah.
And I think this year, you know, all the preparations are in place. If there's a change to that, maybe we just postpone it by, you know, by a month, have it at the end of August or beginning of September, because I'm sure we'll get back to 3, you know, level 3 and 2. Yeah.
Yes. Patrick, you can take it that we want it to happen.
Yes.
And you know also that I feel strongly that we should cooperate more with SAMO. We don't just want to run after the Olympiad guys. Yeah. We want to plan together with them.
Yes, true.
Because it is not ideal. The one does this and the other one does something else.
Yeah.
Because we have the same conditions. No, not quite, you know, primary school, high school, but yeah. Nico and everybody can rest assured we're going to try our best to make it happen. But you realize we must know that it must be safe. And so if there are, you know, level 5 stuff is heavy stuff, and I note that people are saying close the schools, that from my perspective would be it's difficult. I don't know. For example, is sports are sports meetings going ahead? You know, if you're not having sports meetings or whatever, it will be very difficult to have a mathematics challenge. Everybody together. Blah blah blah. Yeah. Okay, we'll follow up and keep everybody informed.
Yes.
So we first have to hear what our president says, and what the teacher unions, of course, seems they are very enthusiastic that the school should be closed. Yes.
Yes, it's Tobega. I just wanted to say that my only concern about keeping the same date is that I know that parents are very nervous. So even if we're not on level 5, but parents will be very nervous to send their children to a venue where, you know, you've got students from all over Gauteng, for example, the Gauteng team. So I would still suggest that I think for most parents and students to feel comfortable that maybe we should look at postponing the date and choosing a date in summer or spring where people are more comfortable to be mixed with, you know, people from other places.
Yeah. So they should write outdoors. Yeah, sorry for making a joke about it. Yes, as we say, Tobeka, we are aware of all those things, and so you know, SAMF with both the Olympiad and the challenge will work very hard on these ideas. We really want it to happen, but we cannot take chances.
Yes, of course. Yeah, one thing we need to know that we are not going to take just a unilateral decision about it. We are going to be looking at all other factors that affect it, including parents, including schools closed or opened, the situation as shall be announced by tomorrow, and we'll be looking at it. And you must know that just postponing the final round has got a trickling effect in terms of the hours and other stuff. So once we postpone everything else, they have to be postponed until the end of the year. The fortunate part of it is that under lockdown, a lot of activities can take place online. So it's not going to be such a big train smash. We can still, work around the timelines that we have. Like Alvin has said, just be rest assured that we are not just going to take a unilateral decision. We are going to look at all other factors and also be safe at the same time.
Okay.
Thank you.
Okay, anything else? Okay, so we will be communicating with you, and I have an idea, but I don't want to put it on the table now. Just do like simple activities that I think we can do with the children. For example, if I now continue, I assume that this is on your screen, clever counting. This, as a matter of fact, is the grade 4 teacher's guide. The right-hand side is the learner's text, and the left-hand side are notes for teachers. And so you see, these structural things that we're talking about is we start with children and say it's not such a good idea to count 1, 2, 3, 4, 5, 6. So we encourage children, and we discuss this. These are children's work that we are sharing with teachers, that, they can group the counters in different ways, and so they can count in multiples. So this is grouped in 5s, so it's quite easy to count 5, 10, 15, 20, 25, blah. And in the end, so 5, 10, 15, all the way up to 50, and then 54, because the side has 4, or something like that. And we consistently do that, and we are saying there in grade 4, do not count. And then here it seems like we're saying calculate, but we are really saying do not calculate. We're saying here, do not calculate. The method, the plan, here at the bottom right, is the important thing. You can calculate later, or even use a calculator once you have written down your plan. So we're pushing the idea of a plan. This is a very important idea. Without doing it, just describe how are you going to do it. I'm going to count in 5s, or in the end, like on top there, you see the number of beads is like 8 plus 8 plus 8 plus 8 is 4 times 8. So instead of counting 8, 16, whatever, if you can start saying it's 4 times 8 and know your tables, then we are starting to talk structure. And so that was the first page. Then here on the left-hand side is the teacher's guide. I trust you can see that how we're trying to help teachers there with structure of what are we seeing. For example, I think that is in question 1. Here on the right-hand side, growing patterns. And you see this green and pink thing, just simple arrangements. Picture 1, picture 2, up to picture 5. And we ask, can you describe picture 6 and 7 in words? Can you draw it? How many squares are there in picture 6 and how many in picture 7? Then we say, can you describe picture 60 and 70 in words? Do not draw them, imagine them, see them in your head. Calculate the number of squares in picture. Well, we're actually more calculate here than I would like. But children easily see this structure and see on top and bottom, there's an equal number of, let's say in picture 8, you've got green 8 and 8, plus 1 for the pink. So if we now ask for picture 60, it will be 60 at the bottom, 60 greens at the top, and 1 on the side. And whether you now start saying 2 times 60 plus 1, or you're saying 60 and 60 and 1, that's fine. That is describing your plan. It is really handling expressions as objects. And so you see here in the teacher's guide, we have the structure. The idea is to see the structure between 2 times 1 plus 1, 2 times 2 plus 1, 2 times 3 plus 1. The structure in the beads is about what changes and what does not change. And so generalizing here in this table is really serious mathematics. And so you can now see for yourself that if we continue in the same way, again, we're helping teachers with children's work here on the left-hand side. And you see that we ask simple things like pictures like this, and we ask children, just like just now, to describe what they see, to draw the next picture, to describe what picture 60 will look like, to calculate the number of beads in picture 60. And all that, to my mind, is, and here are some more examples of very simple ideas that will help children to start working with structure. So that's a grade 4. That's a grade 4 example. And I hope that if I click here, you now see a different one. Do you see grade 6? Do you see our T's here on the left-hand side?
Yes, we do. Yes, we do, Alwyn.
Thank you. And as you can see there, we are doing there exactly with the grade 6s that we tried to do with you this morning. And so there are 5 T's. And we say, the children will say, they see 5 and 5 and 5 and 1 yellow. And they see 4 and 4 and 4, and then we increasingly write this as expressions. So those stuff that I wrote below each other are just here written next to each other. And we use color to try to create the difference between constants and variables. And our experience is that this, like this T and this X, here we describe how to do it for the X, and we let children do it. This, we put it in a flow diagram, and there's an L, and there's a V, and there's LT, and a C, and an L. And children can work with these structures. So generalizing these structures. So we are not saying teach them formula. We're saying the very basics of constant and variables is at stake here. And so it's too quick to analyze these now, but some of these pictures are very interesting, and children learn quite a lot from this, what happens to there, what happens to there, etc. And in the end, we make tables of values. So you see there are multiples of 3, there are multiples of 2, there is a more complicated sequence. So how are we going to describe that sequence? So all these examples are done with our children, and as far as I can tell, they do quite well in it. So we will, using similar examples that we're going to try to do with our 3rd round qualifiers, some of the top children, and see what we can learn from that and what they can learn from it. And so here when we say make a plan, we try here. I don't have an example here. It's in the next section. We try to describe it not as formulas, as if you know your caps in the primary school. We're not really pushing it as formulas, but we write it as flow diagrams. So if you make a flow diagram like times 3 plus 1, then that will describe how you get the different T's. Times 3 plus 1 flow diagram, and we've got nice flow diagrams. So flow diagrams is the way that we represent our plans and our formulas at this level, and that is the beginning of algebra, of understanding that our input values are variables, our output values are variables, our things there in the middle are not numbers, it's called operators. So multiply by 3 plus 1, the operator. So we've got that whole idea of input numbers, operators, and output numbers, which of course is the function idea in high school. And with examples like these. You make a flow diagram to show the number of beads in the fifth, the fourth of these, like this, will be a simple times 3 plus 1 flow diagram with input values 1, 2, 3, 4, 5, and output values 4, blah, blah, blah. Okay. I thought I would just flash this and say, this is what the background what we're trying to give our learners, and then to build on it. So from our perspective, it's structure, structure, structure. Whether they will be as formal as this, or whether, look, it's so simple. This is the fourth one, 4 purples at the bottom, 4 purples at the top, 3 in the middle. That 3 is not just a number. The 3 is 1 less than the 4. So the fourth one has 4 at the top, at the bottom, 4 at the top, and 3, 1 less than 1. Here likewise, 3 and 2. 2 and 2 and 1. Oops, I don't even know this one would be 1 and 0. Complicated, there it is. So, come now guys, when you have an open mind, most people will find it very easy to see the pattern in these geometric patterns like this, and to then develop the most fundamental ideas of input variable, output variable, and plan. What's your plan? I'm going to add the bottoms and the tops and 1 less in the middle. And these are all like this. How they vary, this is the teacher's guide, this is the children's work. And so there you see again that you have multiples of 2, and that is just a constant value, etc. Okay, I leave it at that. I can, if anybody says that they have a need of these textbooks, I can also arrange that we put it on the website, the LMS with Limina, no problem. It's freely available. All right, no questions or discussion. Okay, then I briefly look at the last piece, just for us. Okay, what do I want to do? Share screen. Right, let's do this one. Okay, we're saying that something like this picture here, there are actually 20 such small rectangles. And we ask a question like, how many rectangles of all sizes are there in the figure? Or in a figure with 15 small. You see, this is how we try to do variables. There's not just one question you must answer it for 20 small rectangles. You must find the structure that enables you to generalize. So after you did 20, 15 should be a walkover, and 234 should also be a walkover. If you're doing arithmetic, if you're doing calculation and not structure, then each one of them is a brand new problem that's going to take ages to calculate. Okay. Now, in presenting this, again, I am concentrating not on the answer, but on our thinking, and I say we always have 2 approaches: an induction where we work and we build it up 1, 2, 3, 4 like in a table, and a deduction where we take a special case and we study the structure to understand it better. So for a maths educator, it's not how do you get the answer, it is how do we do it in this way and how do we do it in this way, induction and deduction, and what's the relationship and how does it all stick together. And so I'm just going to go run through it quickly. I'm going to do 3 of these. You please work with me or work ahead of me. I'm now going to say, we're going to first start with induction. Do you understand? Can you sit up right there? We're going to build it up systematically. 1, 2, 3, 4. It means I'm going to make a table. And I'm going to make like a number pattern and see where we go. Then we must have control. Do we think it's a good idea? Or should we try something else? What else can we do? Going. So that really means that we have this plan of making such a table where the number of small rectangles is given by n, and the number of all rectangles is given by rectangles n, like this. And so we're going to go 1, 2, 3, 4, 5 and see if we can get patterns that will help us to say for 20. After we say for 20, we also want to say for 235 and for 46 and for n, but we're not going to say n. So we have to develop this. It's not given. So things like this is not in the syllabus. This whole idea of trying special cases, making it, etc. This is what to do when you do not know what to do. Come on, guys, it's not so simple. How many rectangles? Now, I can just say lots of strange things happen. I work with teachers who says, okay, there are 20 small ones. Let's call them size 1. And then they say, okay, 20 divided by 2 is 10. And they say there are 10 size 2s. No size 3s. 20 divided by 4 is 5. So there are 5 size 4s. Well, that's of course typical. Now you must investigate it. Of course, that is wrong, because if you would do it like that, 20 divided by 2 is 10, then you would just have, must I use the writing? I don't see my pen. I can't write at the moment. Then you will have a 2 by 1 and another next to it 2 by 1 and another 2 by 1. So we're saying there are 10 size 2s, but that's of course not true, because in between there are lots of different sizes. So you'll see now if we work with that. That is a misconception. So here we go. If you're going to build it up with induction, you start with 1 and you say there's only 1 rectangle. Then you take 2 and you say, okay, if I have 2 small ones like that, then how many rectangles do we have? Of course, we know we mustn't say there are 2, but about. So we actually have, if all this is important in order to communicate. If we call the one A and the other one B, then size 1 we've got 1 each. A and B are, and then size 2 is AB. So that gives you 3. There are 3 rectangles in this figure. It looks like 2, but it's 3. Don't forget the big one. So we write in 3. We're definitely, we know, through induction can't now say what's the pattern. So 3. There are 3 small ones. We want to know how many rectangles. What's the question was of all sizes. What sizes? Well, if we call them ABC, then there's a size 1, a size 2, and a size 3. There are 3 size 1s, you A and B and C. Look at, if you use symbols, then the computer can do it. It's so easy to describe. AB is a rectangle and BC is a rectangle. A size 3 is the whole thing, ABC. So this is so important to be able to use symbols, and then to use symbols in order to think. It helps us to think. It's a thinking tool. And so we fill in the 6. Let's go for 4. A, B, C, D. Obviously there are 4 small ones, but it's much better to write and be systematic. Size 1, 4. Size 2, do we understand? Size 3, size 4. I trust that you understand my notation and exactly what it means. So this geometric, call it intuition, is very important developmental work that we must do. So first of all, we must get that gives us 10. And of course, guys, you all know now that here we have again this, I'm sure we've met it before, and so that's not so easy at all. So that's 15, and if we now want it for 20 or whatever, then we can say that's plus 2 and plus 3 and plus 4 and plus 5, but we cannot go on like that forever. And at the same time, look, you can be lucky, you can be very clever, but it's not so easy to find. Remember, we've got these two ideas. The recursion is this relationship between this, in the sequence, and function is the relationship between the two sets. What do I do to the 2 to get 3? What do I do to the 4 to get 10?
Mr. Alvin, Mr. Alvin,
Yes, I'm listening.
I have a question here, which I
Yes.
don't know. From a learner perspective, the rectangle number 3, you said there are 6 rectangles.
Yeah.
Looking at the diagram as a learner, I would argue and say that referring to the second rectangle, that this is not the rectangle, it's a square.
A square. Sorry, is that what you said? You broke up a little bit.
I wouldn't say yes. Look at yes. For rectangle number 3, you have A is a rectangle, yes, B and C is a rectangle. Now, the second one, AB and AC are not rectangles from a learner perspective.
What learner perspective? What's
Looking
wrong
at
with
the
AB?
diagram,
AB is a rectangle. AC is not a rectangle.
AB and BC is not a rectangle.
Why not?
To the diagram. A rectangle, you have 2 opposite sides equal from the properties of quadrilaterals. And square, all sides are equal.
Well, you must have very good eyes. It doesn't look to me that it has the same size, but of course this is an old problem. And so it is incumbent on us. It's not very easy, but of course a square is a rectangle. A rose is a flower. A dog is an animal, no matter if it's special. So we have a isosceles triangle, but it's still a triangle. We've got an equilateral triangle, but it's still a triangle. Sorry, I don't want to. It's always a problem, guys. It's always a problem. It has to do with, we are guilty in any grade 1 class. The syllabus says, and in every grade 1 class there's a picture of a triangle. What kind of a triangle? An equilateral triangle. All triangles are equilateral. There's a square. There's a square, and next to the square is a rectangle. So they're different. And then there's a circle. So in grade 1, we've got a circle and a rectangle and a square and a triangle. And they're all, sorry, I don't want to go there now. But of course, we simply with time have to develop the notion that it's not looks. It is actually by definition that a square is just a special rectangle. A parallelogram, a rectangle is a special parallelogram.
Yes.
Okay. So there is no escaping here. That we just cannot hear.
Okay.
We cannot at any level say, I appreciate you say from the learner's perspective, but logically, you have to engage this idea. I don't want to now, I have several sketchpad activities where I take different figures and I move them. So again, I say we simply have to grow up with the idea.
But I do think, if you're in a classroom, we negotiate it. But I wonder if he means if it's now a challenge and we don't necessarily want to assess whether learners know a square is a rectangle, then is there any harm in calling it blocks?
Oh, the words.
Yeah, but I think Alwyn and Erna, I
because
think
it,
yes,
it will confuse. It will confuse.
The idea that there are learners' perspectives. Learners' learner perspectives are actually drawn from experiences that they get as they engage with their teachers. And in this case, it's not going to be just one teacher. It will be in the whole years in which they have been learning mathematics. And the idea I'm getting from Alwyn is that if we did not look into classes of quadrilaterals and try to find ways of classifying them in order for learners to be able to understand what is a sufficient definition of, say, for example, in this case, a rectangle. Dr. Oliphant, what you just said, you said a square, you said a rectangle has two opposite sides that are equal.
Yes, the properties of square and a rectangle, they differ.
Yes, but can I just finish?
Yes.
The square also has opposite sides that are equal.
Yes.
Which qualifies it to be a rectangle then. So, and I think it is along those lines that we haven't really explored as many classes of, which is there in the curriculum, by the way. There's a point where they actually a year in which they focus on quadrilaterals only. And it is in that year that this kind of classes of quadrilaterals in which you can actually look into this kind of things and what makes a sufficient description are important. And the idea that the learner's perspective is that the square is not a rectangle is actually a teacher's perspective. Thank you.
Can I add something again? Remember, we are teaching learners the properties of those quadrilaterals. Now, it will contradict the teacher if you had to teach now learners the area and the perimeter of both quadrilateral, the square, and the rectangle. I don't know. I'm understandable.
We're not talking about perimeters at all.
No. I'm saying I'm taking an example now.
Yeah,
I'm using.
I shot myself down, of course, because I now came with look what children are doing and look what they can do, etc. Well, you know, for me, the course really is all about teachers, and so all those previous activities, I would say, you know, I think are great learner activities. Personally, I would not think that this is a primary school learner activity, but I'm using it with teachers. But Manari and myself, make no mistake, it's not so easy to say that, you know, by definition, the opposite sides are equal, etc. This is very difficult because of their, you know, Van Hille and all that. You know, understand when people are at Van Hille level 0, when the visual determines what they see and not the definitions and the properties of the figures, it's very difficult. I can just say, before I retired, when my students, high school students had to give lessons to children, I said, we don't give easy lessons. We don't play shop. You must take the challenge of only teaching something that is difficult. And so I had my best student in the class said, okay, he with a grade 9 class, he's going to convince them that a square is a rectangle. And I tell you, at the end of that period, the children convinced him that a rectangle is a special square.
Square, yes.
It's because the properties, you know, what properties are kept. You know, they have the same properties and they have different properties. And so if all squares are a subset of the rectangles, they are sets. But then the properties are the other way around. The square has more properties than the rectangles. It has equal sides. It has a diagonal at 45 degrees. And so you can that is so. I think when we work with teachers, we must make time. I nearly feel challenged to try and search my computer and come up with my attempts that I am always trying to share with teachers, from using everyday examples like a rose is a flower, this is and then all those relationships between a rectangle and a rhombus and a square and a parallelogram, how do they fit together? That's tough work, but it has to be done. Okay. I would say this is not my intention that damn thing AB must look like a square. But you just cannot escape it. The other example is, for example, we have this example which we ask all the time. We say, okay, the farmer has a sheep pen or a skaapkraal, a rectangular sheep pen. He's got 100 meters of wire. What size must he build the kraal? Well, obviously we think he must have the maximum area. And so what you find is that the answer is that the length must be 10 by 10. Sorry, what did I say? 25 by 25. Length is 25, breadth is 25.
Yes.
That will give the maximum area. And I tell you, every year when we ask that question, before schools closed for the day, I have 5 principals phoning me and saying, but there's a problem, it can't be 25, because when it's 25, it's a square. The question said he wants to build a rectangle. So now they don't want the answer to be 25. I say, what do you want the answer to be? No, they think it can be 26 and 24. But sorry guys, the answer is 25. If the sides are 25, you set out to make a rectangle. But when you calculate the area, it turns out to be a square. That changes nothing. It is still a rectangle. Blah, blah, blah. So, it's not an easy problem. But my intention is not here to go into that debate here. So I'd rather, whenever I would ask this to teachers, I would rather change my sketches or use other words like Erna said.
Yes.
Okay?
Okay, sir.
Thank you. We're finishing here and saying, yes, but that's not so easy. And so I say, do not do that. That is a very difficult 1, 3, 6, 10, 15. I'd like to really do it with you because there are some nice things. 3 times 2 is 6, 5 times 3 is 15, 1 times 1 is 1. So that's times 1.5, that's 2.5. We can do wonderful maths here if you really put your mind to it. But for the moment, I'm saying, no, structures, not answers. Those answers, 3, 6, 10, 15, is a problem. But why do we do it? I'll go back and say, may I remind you? I'm going, what now? Back. Look what we had. Next. We had 1 plus 2 plus 3. Why do we insist on saying it is 6? The structure is 1 plus 2 plus 3. And it says everything. It says there are 3 size 1s, 2 size 2s, and 1 size 3. 1 plus 2 plus 3. Then for the next one, the structure is 1 plus 2 plus 3 plus 4, but we insist on adding it. I'm back to do not calculate. So if I rush forward so that we can, then I say, for heaven's sake, why 3? Why not 1 plus 2? Why 6? Why not 1 plus 2 plus 3? of course, what we now need to do is to generalize this. Can you go from 5 is 1 plus 2 plus 3 plus 4 plus 5 to claim that for 20 we'll have 1 plus 2 up to 20? That's the structure. Of course, I see it as the answer. Other people will want a numerical answer. I'm not even going to do it. You realize that I'm going to say it's 1 plus 2 up to 19 plus 20, but you can use Gauss. 1 and 20 is 21, 2 and 19 is 21, 10 of them. So the answer is 21 times 10. Structure, structure, structure. So whenever I'm working here, we have this problem that we still need a shortcut to do this 1 plus 2 plus 3 all the way to 100. I'm not going to do it. We simply add the first and the last, or write it as we did this morning, repeat it in the opposite order below it, and think a little bit. But I hope you understand the difference between that 6, 10, and 15 and this, not calculate. I'm going. Right, now I'm going to, that was working inductively. When we worked inductively, we first made a table for 1, 2, 3, 4, 5. We tried from our database to generalize, and that was not so easy. So let's try the other thing. Let's go for deduction. That means reasoning. But we take a special case, but we must see the general in the particular. That means there must be the numbers that you choose mustn't. It must be such that you may as well have chosen other numbers as well. So I'm taking 6 as a special case. As you know, we're lazy. We're not going to do the 20. Afterwards, it's easy, but not in the beginning. And I'm going to do all our heuristics. I'm going to introduce some notations and symbols, special cases, a table, find a pattern, generalize, explain. So there we go. If we introduce some notation, if we make a table for this time, I'm going vertically, a table for the region, the size 1, size 2, size 3, if you know what I mean by that. Obviously, for size 1, there is each one of them. A, B, C, D, E, and F, size 1. There are 6 of them. For size 2, well, let's make sure I understand the problem. What does size 2 mean? It now means that I can take this AB and this CD and this EF. I said that was what many people do, like 6 divided by 2 is 3. Then you would have just those 3 size 2s. But that's, of course, not correct. Surely, AB is a rectangle, BC is a rectangle, etc. So there are 5. And then size 3, there are 4. And size 4, there are 3. Size 5, there is 2. Size 6, A, B, C, D, E, F. Not a very good notation, but you get my drift. There's 1. Now, why did we do this? Remember, our question is those 20 small rectangles. How many total? Now, the mistake that we make again is to go for calculation. If we say 1 and 2 and 3 is 6 and 4 is 10, is 15, is 21. And if we say for 6 rectangles, we've got 21. For 20, I just do not see how we can generalize that. There is no pattern between that 6 and 21 and 20 and answer. So over and over and over, we have this problem where we want to calculate. Why on earth would you want to calculate? Why not answers? Use structure, generalized structure, not number. So the structure is for this 6 rectangle, size 6 rectangle, the answer is 1 plus 2 plus 3 plus 4 plus 5 plus 6. That is the structure. You must understand why it is 6 and 5. 6, because there are 6 size 1s. Why 5? Because there's 5 size 2s. Why 1? because there's just one size 6. You should see that even without the table. And now, if you understand that we are using this as structure, then we must learn how to generalize this for our original question, which was for 20 rectangles. Surely, how about that? I hope this is okay with you, right at the bottom. If that is for 6, we know why it's 1 and 2 and 3 and 4 and 5 and 6. Then for 20, it will likewise be 1 plus 2 plus 3 plus 4, all the way up to 20. You realize, of course, it is the same answer we had in the previous. So here, deduction and induction gives me the same structural answer. But the approach is different. I am generalizing this whole thing, while here with induction, I'm trying to go back. Am I stuck again? Sorry. Again, structure, structure, structure. And that's the last slide, therefore it goes black. I'm just going back and saying here, remember here we built it up from 1 to 5 like this. So the whole reasoning is different, but the result is the same. Okay. I'm going to do the second last one. If there is questions or comments. Again, I'm going to say, you realize that this 1, 3, 6, 10, 15, these are the triangular numbers. I think I'm going to do it just now. These are the triangular numbers, and that is grade 11 and 12 work. How are we going to do it differently from this in primary school? I don't know. Okay, I'm going out here. I'm going to I think I may as well. I must open a different one. I tell you, I'm going to skip squares. I'm going straight for this, like, probably final one. Okay. It is sharing. So here we go. Okay, here we go with our same 1, 3, 6, 10, 15, 21, 28. And we have a specific question here. Because remember, this is what we're all about. We're only interested in interesting things. And we're inquisitive. And so, if you just give children a chance to play around, they will come up with wonderful things. So, one thing here that we're asking very, let's just go, I hate this, but I'm asking a sort of a direct question. Investigate the sum of 2 consecutive numbers. Of course, you must understand all the words, etc. You must understand this definition. It is, of course, plus 2, plus 3, plus 4, plus 5, plus 6, plus 7. And, okay, so again, it's control. We make a plan. We understand the problem, what it means. We must look at 2 consecutive numbers. So 1 and 2 are consecutive. 1 plus 3 is 4. So if we can't bring knowledge that we think is applicable, we have no option really to use induction. So we go again the same, we investigate special cases. So we start off with the first and the second. That's our problem. So that's 1 and 3. We say it's 4. And so we're very systematic. And remember, I'm getting up here. The 4th one is 10. The 5th one is 15. So 10 and 15 is 25. And the 5th and the 6th one, 15 and 21. Now, I'm going to say again, I assume that you understand that this 3 and 6, and this 6 and 10, and 10 and 15, and 15 and 21, these numbers, they cannot tell me what's going on here. Okay, so of course we calculate in between, and so we do recognize these as not just any numbers. These are special numbers, they are squares, and so we give structure. Cindy says the sum of two consecutive triangular numbers is always a square. Now you see, she's finished, but the mathematician now only starts. We want to know immediately, why is that? Is it really so? Remember this morning we had something that was true for 10 cases. Sorry guys, my database is again only 5. I have 5 examples, and Cindy is saying always. But we know having it true for 5 cases is just not good enough. We've got all these examples that is true for 1 million cases, but not true for the next one. We cannot say always. So this is where the mathematics starts. This is where the mathematician starts. We want to know 2 things. Is it really true? We're skeptical. Is Cindy really true? Is what Cindy says true? And number 2, if it is true, why? Why a square? Why not a cube? Why not a multiple of 3? Why not an even number? Okay, well, what to do? Well, it's not that we must remember something. We must be creative. Creative? I don't know. I'm going to say, I think we can try to interpret it geometrically, or we can try to interpret it geometrically and see if it can help. Looking back, why? Can you explain it? Really? Always? Can you prove it? That's the mathematics. Not this answer, which we don't even know is true. Okay, now remember the triangular numbers. A problem posing. Can we predict the 100th triangular number? Do we need it? Can we predict the 60th plus the next one, 61st? You know, I mean anyone. 70, 100, blah, blah, blah. So what can we do? So there's the bare bones. Can we predict this? Where are we going to get it? Surely. The structure here is very simple. But I'm going to say again, this calculation is in our way. So I'm going to say it helps to remove the noise. This is just in my way. If I delete all that, then we really got those 3 columns. It's the first number plus the second number is equal to the answer. The second plus the third is equal to the answer. The third plus the fourth. And so we can see that the first and the answer is the same, 2, 3, 4, 5. No, they're not. It's one more. These are the same, 2 and 2, 3 and 3. I'm not even going to ask. I'm assuming that this relationship is simple enough for us now to complete that if we have those 5 examples. Now, not the answers, the structure. Then that number plus that number. What is this relationship between these sets? Surely, if you look at that, the second number plus the third number is the third number squared, 3 squared. The fourth number plus the fifth number is 5 squared. Then this 60th plus 61st is 61 squared. And if okay, we know that, but we still don't know why, etc. So, of course, if we use the structure, I'm going to say again, there is absolutely nothing in these numbers that can explain to me why it is 4 and 9 and 16 and 25. Why? What strange numbers are these? There's nothing in the numbers. Forget the numbers. We have to concentrate on structure. And the structure clearly is +2, +3, +4, +5, like that. So instead of working with 1, 3, 6, 10, 15, which is really the answers, break up the numbers and say 3 is 1 + 2 and 6 is 1 + 2 + 3. And so I'm now going to represent those numbers geometrically. I'm going to think geometrically. Of course, it is because we have lots of previous experience of this. We've done several like this. So, for example, if I'm going to say that the second triangular number is 1 + 2, then I'm going to represent it like that, 1 on top, 2 at the bottom, because it will enable me to say the third one, 6, is 1 + 2 + 3. I trust you understand that I'm not working with 3 and 6 and 10 and 15. I'm working with the structure, 1 plus. Now, the fourth one is 1 + 2 + 3 + 4. And the fifth one is 1 + 2 + 3 + 4 + 5. And now we go back to the first one. These are triangular numbers. This is why they are triangular numbers, because we can arrange them in the form of a triangle. Those 1, 3, 6, 10. Now we just add 1 with it. It's not a triangle, but it's like a natural sequence. The mathematician often generalizes like that. Okay. So this now is a geometric representation of the first number, second, third, fourth, fifth. First, second, third, fourth, fifth. Now, what are we talking about? We are talking about the sum of two consecutives. So the question remains, why are these squares? And it's not in the numbers for the fifth time. I'm now taking a special case, namely the third and the fourth. I'm giving them different colors. The third is 1 + 2 + 3. The next one, the fourth one, is 1 + 2 + 3 + 4. If I add them, I'm merely pushing them together. And I'm doing it like this. If I take this green triangle and I rotate it 380 and I fit it on the side here, then it will fit here exactly to form this 4 by 4 rhombus, or 4 by 4 parallelogram. Of course, if you want to now think of a square as a geometric figure, then I can just push at the top, and then I'll push it so that it becomes a square. You just have to push it over that it's not leaning but standing straight. And I trust if you now, the children, need lots to spend some time and to think about how this second number will always fit against the first number. So here you have an example where the first and the second, or in this case the third and the fourth, 6 and 10, that is 6 and this is 10, gives me 16. So that becomes, I see now a structure 4 and 4 and 4 and 4, or call it vertically 4 and 4 and 4 and 4. And now if I look at the geometric representation on the right, which is a geometric square, of course, how many? You don't count 1, 2, 3, 4. You use structure, clever counting, like we're teaching the children. Clever counting. How many counters, or call them counters, stones are there in this figure? It's 4 times 4 is 4 squared. So this can now easily be generalized. Just add 4 there at the bottom and add 5 at this bottom, then you've got the fourth and the fifth. And so no matter that you choose specific ones, you should see that this is always going to happen. Always we're going to manage to fit the second one on to the first one to form a rhombus And if you push it a square, and therefore that explains why it is always a square. Square, 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 square. Okay, I did that with geometry. But now, having worked here, it gives me an idea of how I can do it numerically. If I do it numerically, again, I'm going to do exactly the same. I'm going to break up the numbers. I'm not going to work with 1, 3, 6, 10, 15. 1, 3, 6, 10, 15 can tell me nothing. It's just numbers. But if I use the structure, then 3 is 1 plus 2, and 10 is 1 plus 2 plus 3 plus 4. So here we go. If I add the first and the second, then the first is 1. I just want to see if I can write here, but no. Just give me a moment. Here we are. I'll go for it. Guys, this... Oh, 1 plus 3. So that's your 1. But now I'm not writing 3. I'm writing 1 plus 2. And if I continue without deleting it, then if I group those, if I group the 1 and 1 is 2, and then I get 2 plus 2, and likewise, if I take the second and the third, instead of saying 3 plus 6, I'm saying 1 plus 2 for 3, and I'm saying 1 plus 2 plus 3 for 6, but then I group them differently because the order doesn't matter and the grouping does not matter, and therefore I go for 1 and 2 is 3 and 2 and 1 is 3, and the 3 is left there. That will give 3 plus 3 plus 3. Obviously, let me just get down here. There we go. 3 plus 3 plus 3, and here we will similarly group them as 1 plus 2 plus 3. Guys, you understand that this is exactly what we did this morning, namely that grouping that we are using there is exactly the same as changing the order and writing them below each other. It's exactly what I did to 78 this morning. But if you want, I can group them horizontally, and I'll get 4 plus 4 plus 4 plus 4. And of course, we're now going to give structure. We give structure. This is what algebra is all about. We're not going to work with this sums 1 plus 2 plus 3. We're not going to work with 4 plus 4 plus 4. We're going to work with 4 times 4. 3 times 3. That's finished. And there we go. To my mind, and I hope to your mind, this explains quite clearly why the sum of any of these two consecutive numbers in this sequence will be a square. It is again where we started last week about the conservation of a number by Piaget's idea, and we have the order doesn't matter, the grouping doesn't matter. So the moment we break it up and we group them, we see that we really have squares. So we're working with the fundamental definition of a numerical square. 2 times 2 is 2 squared. 3 times 3 is 3 squared. So everything is good mathematics. Can I finish here and say again that we could simply add the numbers and say there, it's a square. But we're answering a different question. We are not coming to discover that the answer is a square. It's obvious that the answer is a square when we add. We are explaining why it is a square. And to do that, we need structure. And in every case, we use structure by not saying 3, but saying 1 plus 2. Not 6, but 1 plus 2 plus 3. So it's unfinished calculation. And that is where the mathematics and the algebra lies, is in this ability to look at with different eyes at these numbers to help you understand how numbers behave. And, you know, again, apart from being inquisitive and skeptical, I must say, I also love the patterns. So we appreciate the beauty of mathematics in this way. Guys, I'm going to stop there and say again, it's open for discussion. And I'm just saying that I've again tried over and over to show that calculation cannot explain, does not help us to explain, and cannot prove. So there's a big difference between getting the answer and saying I'm finished and getting the answer and saying now we're beginning. Our activity is now different. We're explaining and proving. And for that you need structure. I've never given a definition of structure, but I trust you understand it most fundamentally means the unfinished calculations. Just now, every time here, my structure was like 1 plus 2 plus 3, or 3 plus 3 plus 3. That's my structure. Not 9, not 16. Okay, this is quite beautiful and quite interesting that we can work with the triangle. So this is a very important sequence, the triangular numbers. It's got wonderful properties which we can explore and explain and prove and appreciate. Right. Is there any discussion, any comment?
Yeah, I enjoy attending this workshop.
I'm glad you but remember this one, just keep on working on it. And that is why I will clean up my PowerPoint a little bit and share it with you. That means when it comes to you presenting workshops, oh yeah, I'm now at the wrong one. I wanted to show the first one. Sorry, I just want to, I'm not sure, let me just, I think I stop share and then I find it again. I want this one. So if I go there and I go here, then I'm on both these slides saying that note this PowerPoint, many people don't understand, this PowerPoint is not for scrolling through and it's not for printing. You may have noticed how the things are on top of each other, and so it's not like, for example, people do this and then I'm scrolling. I'm rolling my mouse button, and then you can look at it. But surely I take it that you understand that all those things of mine are on top of each other. It's not clear. This is a total mess that is here in front of us. And so you should not be scrolling at this thing here in this mode. You should be scrolling here that is called, here at the bottom, this is a slideshow. So if I open the slideshow and I click, then these things appear one at a time. And so you cannot scroll through it. Please don't do that. It is the way I work with this is that I put these things on top of each other all the time. So it's very important to to work. Just click, click, click. I am at the moment left clicking, clicking, and this is opening, or I can on my keyboard go previous and next. And if you just scroll, then everything here appears at the same time instead of one after the other. You understand? These things are all sitting on top of each other. That piece and this and at the bottom. And likewise here, everything here is on top of each other, and you cannot look at the pieces. So click, 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 click through it. That is the intention. Not to scroll through in a different mode. So there are two ways when you are here. It's either, I never use I'm a keyboard, I'm a mouse man. So I think view, I don't even know, transition, slideshow. There's a slideshow up there that you're either a menu person or you're a mouse person. I'm a mouse person. I click here at the bottom, there's slideshow, written slideshow. I click there, but other people do slideshow up here and it says start from the beginning, start from the current slide, blah, blah, blah. Yes, this is very nice. I never worked there. So, yeah. But remember, you must work in
You can transfer it to PowerPoint.
Say again?
You can even transfer it to PowerPoint.
Yes, I all the time, like this morning when I worked, I opened two PowerPoints next to each other with view and arrange all. And then I copy this from the one to the other as I need it. So this was in the one PowerPoint and there's another PowerPoint. So I just copied this whole slide onto this one. So you can do all those things. So understanding the differences between this representation and this, etc., is very important. For the moment, I'm merely saying, please, I must go there. Read that piece. Click, 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 and not scroll. So it's very important. Otherwise, you have none of this animation, none of this interaction. And so I uncover it bit by bit. And so you can talk to it bit by bit. You shouldn't have the whole screen there at the same time. This already is too much. Like here, instead of putting the whole page at the same time, you first do that bit, then that bit. But if you scroll, you would have them all at the same time. So that's quite important for PowerPoint. Guys, this now for the moment is all. It was heavy stuff to take 2 Saturdays instead of a full-time weekend. The other course we're running at the moment is 10 weeks long, of about 3 hours a week. We wanted quicker results, and therefore we opted for this package. And I hope that you found it useful and that we will now continue working together with you, presenting some workshops, and so that other people can learn from you. We're about done, but the floor is open for a last question, input. Nope.
Job well done, sir.
Alvin?
Thanks to your presence. Hello?
Yeah, no,
Mr. Alvin?
Mine is to appreciate and to say thank you. And when we talk about revolution or being a revolutionist in the subject, I think it's quite clear. What your intentions are very clear, and we definitely hope not to disappoint. And I think it's
Yes, sorry, you break up there. So I'm saying, guys, this is all about our own professional development. Okay, it's our own professional development. First, we look after ourselves. So if we can appreciate it, if we can see more patterns, and if we can put on new eyes, then we're growing. And that is being human. That makes the difference. So I appreciate, Ste, we come a long way. So it's nice having you. And well, I hope to. I hope that all this level 5 stuff, etc., will go away so that we can have more face-to-face workshops. Going. Anybody else?
Thank you very much, Alwyn.
Thank you, Alwyn. Thank you so much for everything. We've really learned a lot.
Okay, Lindy, we thank you. Guys,
thanks
remember, you have until next. Remember, there's a prerequisite here. I think when you get to the final assessment, you're going to love the questions. They come mostly out of the challenge. They're beautiful questions. They're well formatted. They're well formulated. You have time. So I want you to enjoy writing that test, and it is a prerequisite for you to present workshops to teachers and to children. So I want you, our participants always do well. I know that you will do well, no problem. You shouldn't sweat about it. if you learn the basic heuristics and the basic thinking, it's a walkover. And so, but do not hesitate. My last sentence, Nico, then I'm finished. Okay. Do not hesitate to write it the second time. You may write it 2 times. So if you don't like your first one, go for the second one. You'll get the highest mark of the 2. So even if you do poorer in the second one, I haven't seen that yet. Even if you do poorer in the second one, the highest mark counts. So maybe you're interested. You may do it. Yes, Nico.
No, I just want to find out. So on the same thing, I want to find out: do we sit at one go and do it, or you can do it in stages?
No, you can't. You have to do it in one go.
Okay, sure, right.
Okay.
The moment you start, there's a. Let me just finish. The moment you start.
Sorry.
The moment you start the test, there's a timer running. And it says you have 2 hours and 20 minutes left. You have 2 hours and 10 minutes left. Okay?
Okay, well, that's fine. Looking forward to it.
That is why we give you from now until next Sunday. So please decide that you're going to write it Sunday night from 10 to 12 when there are no children around and no dogs barking, so that you will not be interrupted. So choose a time where you hope you will not be interrupted, Nico.
And load shedding, of course. Check the load shedding schedule.
Yeah, check the bloody load shedding.
Yeah, this is a very busy week, Alwyn.
Yeah, yes. I realize, but we feel that somewhere you must find 2.5 hours, please, in the middle of the night. Somewhere you must find 2 hours. So if that's different for every person, so find your personal best time that you can say you're going to sit down and do it. Okay? And if you have any problems, do not hesitate for a moment to contact me and Patrick.
Can I ask about assignment? Hello?
Hello, yes?
Yeah, you said the assignment takes 20% of the time. So is it possible to, if we didn't do well in the assignment, do we have the supplementary, or we supplement it with the test?
I'm gonna say you shouldn't worry about this. I'll organize it with you personally. Yeah.
Okay. Thank you very much. Thanks.
The assessment should not be a problem for anybody. As long as you bring your best, everything will be fine.
Okay, thank you very much.
It's not an attendance course. You have to work. You have to stretch yourself. It's not, but participation and the assignment and what we call the final assessment, the final test, they together will determine your mark. And I'll communicate everything back to you.
And
Thank you very
Alwyn,
much.
when are we getting our results?
As soon as we've finished, I can't do it before next Sunday night, 12 o'clock. Then it's closed, and then I can look at the marks. And then we go to Patrick and Ellie, and they communicate it to Sachi, and we'll then also give you a SAMF certificate according to your marks, either cum laude or passed or participated. Okay.
And we also
But
want
it'll
gifts
have-
as well, eh, Patrick? One presents and gifts.
One present and gifts. Let's see what you can do, Angelico. Let's see what you can do.
Yes. Okay, guys, let's go out. It's Saturday afternoon. Again, I'm saying I very much value your participants, and I think it's so wonderful that you that you're available in such difficult times, and I really hope that it is worthwhile in all kinds of aspects, from promotion to personal development. I hope you find it worthwhile, and that you'll continue getting your teeth into this. With that, I'm saying over and out. Let's go. It's Saturday. It's weekend.
Thank you very much.
The women's finals.
Please don't forget to send us Limina link.
What about it? Yeah, I did forward it. They'll check if you didn't find. There are 2-3 people who say they didn't find. They'll get the link. They'll fix it, and they'll
Okay,
email
thank
you with a new password. Then use the password, and it will work.
Okay, thank you very much.
Thank you,
Bye,
everybody.
Alwyn. Thank you.
Thank you, Alwyn.
Bye bye. Bye, Ashley.
Bye bye, Ella.
Bye bye.